Hello there and welcome to Life Beyond Seen, where curiosity settles in quietly and complicated ideas drift into something gentle enough to fall asleep to if that's what you need right now. Tonight's slow walk takes us somewhere most of us will never go, yet it affects all of us more than we realise. We're going to spend time beneath Antarctica. Not the shiny icy surface that shows up in textbooks or travel documentaries, but the place underneath all that. The vast hidden ocean that scientists discovered little by little. The one that has been forming questions faster than they can find answers. It's a place that doesn't fit the usual rules we expect from the world. It isn't supposed to be warm in certain pockets. It isn't supposed to have currents that move the way they do. It isn't supposed to hold forms of life that survived in isolation for longer than recorded human history. And yet, it does all of that. Before we drift into that world and the concerns attached to it, I'd love to know something simple. Where are you listening from tonight, and what time is it where you are? It always amazes me how many places come together in this quiet little space. Some of you are settling in for the night, some are tucked under blankets trying to slow the day down, and others might be listening while the sun is bright outside your window. Whatever moment you're in, you've reached this one now, and that's more than enough. If you enjoy these calm explanations that wander through science at a slower pace, it would mean a great deal if you'd give the video a like or subscribe. It helps this peaceful corner find others who might need something steady to fall asleep to, or something thoughtful to help their mind rest. No pressure, of course. Do whatever feels right for you in this moment. Now, let's take our first step toward the southernmost part of the planet. Antarctica is often described as silent, but silence isn't quite the right word. Anyone who has spent time there will tell you it has a sound unlike any other place. Wind moves in long, low stretches. Ice shifts without warning. Snow presses against itself until it settles. But the most surprising part isn't any of that. It's the sound of water hidden far below a frozen layer so thick and heavy that, for a long time, people assumed nothing interesting could be under it at all. That assumption turned out to be wrong. And once the truth started to appear, scientists realised they weren't dealing with a rare pocket of melt or a few scattered channels. They were looking at an entire system, a network of water stretching under the continent in ways nobody expected. Picture a continent the size of the United States and Mexico combined, covered by ice that reaches several kilometres thick in many places. That ice weighs so much that it presses the land beneath it into a bowl, and inside that bowl sits water, not just pools of it, but an ocean in its own right. There are lakes, channels, caverns, and long corridors where water moves as steadily as any underground river. Some of these lakes are roughly the size of major cities, even though they have been sealed off from sunlight for millions of years. Others are shallow and still, containing layers of sediment that settled there long before humans walked the earth. For a long time, scientists believed the ice sheet was mostly frozen solid from top to bottom. Then radar surveys revealed something different, something alive with motion. Water sliding along the bottom of the ice sheet. Water pushing into new routes. Water disappearing into cavities and resurfacing somewhere entirely unexpected. This wasn't a slow discovery. Once the first detailed survey started to map the continent in the late 20th century, the number of lakes kept growing. Dozens became hundreds. Eventually the picture changed from isolated features to a connected system that moved in cycles. A lake would fill slowly under intense pressure until it reached a point where it suddenly drained. The draining water rushed through tunnels under the ice, sometimes travelling tens or even hundreds of kilometres before settling into another basin. Then the process would begin again. The continent wasn't still, it was breathing, shifting, changing. And almost every new measurement revealed something that didn't quite match earlier expectations. Scientists felt excitement, of course. Hidden systems like this are rare. But as the data grew, so did their concern, because the more they learned, the less predictable the whole system seemed. A hidden ocean under Antarctica isn't just interesting, It has the potential to reshape coastlines, influence global sea levels, disturb long-term climate patterns, and alter ocean circulation rhythms that affect weather thousands of kilometers away. And that's only the beginning. Much of the anxiety comes from the warmth in this underwater world. It doesn't come from sunlight. It comes from friction, geothermal heat, and insulation under kilometers of ice. That combination creates conditions that allow water to move in ways that undermine the ice sheet from below. Large sections of ice that look stable from the surface can be sitting on foundations weakened by warm water at the base. And when something that large becomes unstable, it usually doesn't happen slowly. It shifts unpredictably. Scientists don't like unpredictability, especially when it involves a continent full of ice that could alter sea levels for generations. That unpredictability is part of what brings fear into their research. Not a dramatic fear, but a steady, calculated one. The kind that grows every time new data contradicts what models predicted. Every time a glacier accelerates faster than expected. Every time a meltwater cavity turns out to be larger than anyone assumed possible. When researchers describe their findings in reports or interviews, they often choose words that sound calm but hint at deep concern. Words like unstable, rapid changes, limited understanding, and potential feedback loops. These aren't emotional terms, they are technical red flags, and they show just how seriously the scientific community takes what's happening beneath Antarctica. But tonight, we aren't in a lecture hall, and this isn't a rushed briefing or a documentary trying to hold your attention through dramatic visuals. This space moves slowly, one piece at a time, so instead of jumping straight into the biggest risks, we'll build toward them gradually the way researchers had to. Step by step, layer by layer, from the first hints of hidden lakes to the moment they realized an entire network existed. We'll move calmly through why certain findings startled them, why the presence of warm water mattered so much, why unknown species thriving in complete darkness challenged assumptions, and why some parts of the ice sheet remain more uncertain than ever. Not to frighten you, but to help you understand what they've learned and why it matters. When people think of Antarctica, they often imagine a place untouched by time, something frozen and unchanging. But the truth is the opposite. The continent is always moving, not quickly, but steadily, like a machine with thousands of slow-moving parts. Each glacier pushes forward under its own weight. Each layer of ice presses downward as snowfall accumulates over years. Each cavity of water expands or contracts depending on unseen factors deep below. That movement has been happening for millions of years. Humans simply weren't there to witness it. Now that we're finally looking closely, we're realizing that the slow pace is only part of the story. Some changes are slow until they reach a threshold. Then they can accelerate with astonishing speed. The hidden ocean is deeply involved in those thresholds. Understanding it begins with understanding pressure. The pressure beneath the ice is it's enough to melt ice even when the temperature is far below freezing. That simple fact explains why water forms under the ice sheet at all. But pressure alone doesn't account for the complex system scientists found. Pressure creates water. It doesn't create networks. Something else is shaping the routes between lakes. Something else keeps these channels open. Something else moves water into areas where it should have frozen solid. And that something turns out to be heat from the Earth's interior. Antarctica isn't one even layer of ice over flat stone. It sits over a patchwork of geothermal regions. Some areas are warmer than others. Some areas heat the underside of the ice enough to speed up melting. Others create pockets where meltwater stays warm enough to expand the hidden ocean even further. This geothermal activity is uneven. That unevenness makes predicting the future incredibly difficult. A slight change in water flow in one region can weaken a specific part of the ice sheet miles away. A cavity growing larger in the dark can destabilize ice that seems steady on the surface. When you scale these effects across an entire continent, the uncertainties multiply. Scientists have mapped hundreds of lakes and countless channels, and still, they know they've only detected a portion of them. Radar can't see everything. Ice scatters signals. Some areas are too thick for accurate readings. So the map remains incomplete, and that incomplete map means surprises are common. Every expedition uncovers something that shifts the picture. All of this makes the hidden ocean more than a curiosity. It becomes a key to understanding the ice sheet's health, and by extension, the stability of coastlines around the world. If the ice sheet remains mostly grounded and stable, sea level rise continues at a slower, predictable pace. If the hidden ocean changes in ways that weaken major glaciers, the pace could accelerate dramatically. That's the quiet concern scientists rarely state outright, but always keep in mind. But for now, let's stay with the beginning of this exploration rather than jump to the consequences. It's easier to understand the risks once we understand the system itself. The discovery of subglacial lakes wasn't a single moment of shock. It was a long series of measurements slowly revealing that the continent held far more water than expected. The first clear evidence came from radar surveys performed decades ago. Though the images were rough and hard to interpret, scientists saw bright reflections that didn't match solid ice or bedrock. Those reflections hinted at liquid water. But the full significance didn't become clear until technology improved and the same surveys began mapping larger regions with better accuracy. Suddenly, features that once looked like anomalies turned into recognizable lakes, and the number kept growing. Researchers drilled through the ice to reach some of them, a process that required immense care to avoid contaminating ecosystems untouched for millions of years. When they finally accessed these lakes, they found sediments with layers representing ancient conditions. They found microorganisms adapted to extreme environments. They found traces of chemical reactions that didn't match any known surface ecosystem. And they found water that moved much faster than expected once pressure changed. All of these discoveries made the hidden ocean more intriguing and more concerning. Because the more dynamic the system appeared, the more it became clear that the stability of Antarctica's ice wasn't just influenced by climate from above, but by water from below. And that connection has reshaped how scientists look at the continent entirely. As we ease into this long exploration, keep in mind that none of what follows requires urgency on your part. You're not here to make decisions. You don't need to hold any of this tightly. You're simply here to listen while everything settles around you at a comfortable pace. Let the details drift in naturally. Let the edges soften. There's no rush. This is a slow journey into one of the strangest environments on Earth, and we're only just stepping into it. Soon, we'll wander deeper into what this ocean looks like, how it moves, and why its behaviour keeps surprising the researchers who study it. For now, allow this first part to settle in gently as we start moving toward the first real layer of the story, waiting underneath the ice. When people imagine Antarctica, they tend to picture something simple. A flat sheet stretching in every direction, endless white broken only by the occasional ridge or wind-carved pattern. It looks quiet from the outside, almost empty, the sort of place where nothing would bother changing unless pushed by the seasons. But that picture isn't accurate, not even from the first layer down. The surface is a thin veneer compared to the structure underneath it. Once researchers began studying the continent with equipment that could see through the ice, the entire idea of Antarctica shifted. What once looked like a frozen desert turned into one of the most active hidden landscapes on Earth, full of water, pressure, shifting ground, unexpected warmth, and systems that don't behave in ways people assume they would. This altered understanding has shaped the way scientists talk about Antarctica today, and why they're cautious whenever new information comes in. Antarctica's ice sheet is not a solid, unmoving block. It is a large, flowing structure that compresses everything beneath it. The ice doesn't rise evenly. It sinks where it grows heavy, pushing the land below into depressions. It rises slightly when ice thins or slides. These changes might sound small, but they happen across distances larger than many countries. The pressure created by these variations has been building for millions of years, long before humans existed. and that pressure shapes the entire hidden world beneath the continent. At the base of the ice, a different environment begins. Temperatures may fall far below freezing at the surface, but pressure from the weight of the ice lowers the melting point. Even when the ice sits on bedrock colder than most freezers, pockets of water still form. Researchers expected to find some meltwater at the bottom of the sheet. What they didn't expect was the scale of it. Early radar surveys revealed shiny reflections where none should exist. Those reflections soon turned into outlines. Outlines turned into shapes, and shapes formed patterns that kept expanding across the map. Researchers found lakes, some shallow and wide, others deep and narrow. They found channels large enough for water to move freely without freezing. They found cavities that looked stable in one measurement and changed shape in the next. They realised that the hidden terrain was more complicated than most surface terrains on the planet. Antarctica wasn't flat beneath the ice. It had valleys, mountains, slopes, ridges and basins, each affecting how water flowed. These pathways created a circulation system that moved water from one region to another, sometimes passing underneath glaciers that looked perfectly stable from above. As more of this world came into view, researchers began to understand why earlier assumptions failed. They had believed the ice was anchored firmly to the land in most areas. It wasn't. Much of it rested on layers of water or soft sediment lubricated by water. That meant huge sections of ice weren't fixed, they were sliding. The sliding didn't happen quickly, but it didn't have to. Even small changes in movement could shape the stability of entire glaciers. A shift of only a few centimetres each day might sound minor, yet multiplied across thousands of kilometres, it changed the long-term behaviour of the ice sheet in ways that carried enormous consequences. The discovery of this hidden water also revealed that the area was far from lifeless. Lakes sealed beneath kilometres of ice shouldn't have been able to support anything familiar. There is no sunlight, there is little oxygen, there is intense isolation, but microbes were found nonetheless, relying on chemical processes rather than sunlight. Their presence meant these lakes were not temporary puddles. They were long-standing ecosystems that had persisted through countless glacial cycles. The hidden world beneath Antarctica wasn't just a physical environment, it was a biological one. Each organism uncovered there added a new layer to the question scientists were already struggling to answer. The behaviour of the water itself was perhaps the most troubling piece. Water at the base of glaciers can move. That part was known. But movement on the scale discovered beneath Antarctica wasn't expected. When one lake drained, water didn't stay in the nearby area. It travelled long distances along the underside of the ice sheet, often ending up in places researchers hadn't predicted. That meant areas thought to be cold and stable might suddenly receive warmer water. Warmer water is important here not because it's comfortable, but because it melts ice more effectively, especially under pressure. This is the same principle that allows ice to melt on a city street when temperatures hover just below freezing. Under pressure, ice becomes vulnerable. The more scientists saw, the more complicated the system became. The lakes didn't just drain, they refilled. Sometimes slowly, sometimes quickly. The cycles varied across the continent. Some lakes filled over decades before releasing their contents. Others cycled more often. These patterns were different enough that researchers struggled to categorize them. There wasn't a single rhythm. There were many. These rhythms influenced glacier behavior above them, changing speeds, shifting directions, creating sudden accelerations, and altering stress points along the ice. Even more surprising was the warmth coming from below. Antarctica isn't known for volcanic activity in the popular imagination, but geothermal hotspots exist beneath the ice. They aren't dramatic volcanoes erupting on the surface. Instead, they're zones where heat slowly rises from the Earth's interior. This heat melts the bottom of the ice sheet more effectively than pressure alone. It also keeps some lakes liquid even when temperatures above are colder than anywhere else on Earth. When researchers measured the strength of geothermal heat beneath certain parts of the continent, they found readings much higher than expected. These readings explain the size and persistence of some subglacial lakes, but they also raised concerns. If geothermal heat was stronger than assumed, then less warming from the atmosphere would be required to destabilize large sections of the ice sheet. As the water flowed, another detail emerged. It carried sediment with it. This sediment changed the friction between the ice and the ground. Sometimes it allowed ice to slide more easily. Sometimes it piled up and slowed movement. Because water and sediment moved constantly, predicting glacier behavior became even harder. What appeared stable could change rapidly with only slight variations in the system. This unpredictability is what concerned scientists most. They were watching a system respond not to one factor, but to many at once. Atmospheric warming, geothermal heat, meltwater pressure, sediment transport, and the natural weight of the ice all work together in a complex balance. Disturb one part, and the rest shifted to compensate. But compensation didn't guarantee stability. The continent's interior, which is far from the warming effects of the ocean, should have remained relatively steady. Instead, researchers found networks of lakes deep inside the ice sheet, where conditions should have been far too cold for free-flowing water. These lakes weren't small. Some were comparable in size to major freshwater bodies on the surface. Their existence hinted that the hidden ocean beneath the ice sheet might be larger than an initial survey suggested. And because radar cannot penetrate the thickest parts of the ice, there is likely much more water than current maps show. Another part of the hidden world involved the grounding lines. These are the regions where ice transitions from resting on land to floating on the sea. Grounding lines are vital because they determine how much ice remains anchored. If warm water from below reaches these lines, even slightly, it can pull the grounding line back, allowing more ice to float. Floating ice is less stable and more prone to breaking. Once that process begins, it becomes difficult to reverse. The hidden water system beneath Antarctica interacts with these grounding lines in ways scientists didn't fully understand. Each discovery suggested the potential for rapid changes that weren't included in earlier models. The hidden world beneath the ice is also shaped by the continent's bedrock. Some regions sit far below sea level, others rise high enough to act as natural barriers. As water flows, it follows these contours, often collecting in basins deeper than the surrounding terrain. In some cases, these basins stretch hundreds of kilometers. Filling and draining them affects the ice above in ways that ripple outward through nearby glaciers. This interaction between ice, water, and ground creates a constantly shifting landscape. While the changes may be too slow to notice in real time, they accumulate steadily. Over decades, small shifts grow into significant alterations that reshape the continent's structure. Scientists study these patterns with satellites, ice-penetrating radar, seismic sensors, and computer models. Each tool reveals a different part of the story. Satellites track changes in surface elevation caused by water movement below. Radar outlines the lakes and channels. Seismic sensors pick up vibrations caused by ice shifts, cracks, and sediment movement. Models attempt to put all the pieces together, but even with these tools, the full picture remains incomplete. The hidden world is simply too large, too deep, and too complex to map fully with current technology. This uncertainty is one of the reasons researchers speak cautiously about Antarctica's future. They're not simply unsure about melting rates, they're unsure about the structure beneath the ice. Many of the processes shaping it occur far below the surface, shielded from direct observation. Even small errors in estimates can lead to large differences in predictions. The hidden world beneath the white silence doesn't behave according to simple rules. It behaves according to interactions that are still being uncovered. The silence people imagine Antarctica to have is misleading. The continent is full of movement. Ice creeps forward, water slides beneath it, sediment shifts, cavities expand or shrink, and deep currents continue carving new paths without sunlight, sound, or witnesses. All of this happens in a region that appears frozen in time from above. The contrast between appearance and reality is stark, and it's one of the reasons scientists have become increasingly aware that the hidden world under Antarctica may be one of the most important environments on Earth to understand. As we move further into this exploration, we'll continue following the path scientists took as they uncovered more of this submerged network. Each discovery builds on the last, and each new detail adds context to the concerns shaping the scientific conversation around Antarctica today. The hidden world doesn't stand apart from the surface. The two are bound together, influencing one another in ways that reach far beyond the ice sheet itself. With that in mind, we can ease forward into the next part of the story, where the water begins to take shape not just as scattered lakes but as a system with a long and complicated history waiting under the ice. When scientists first began to understand that Antarctica held liquid water beneath its ice, the idea felt almost out of place. Water under such extreme cold seemed improbable, and an ocean hidden under kilometres of ice felt more like the premise of a speculative novel than something belonging to the real world. Yet each new survey, each new measurement and each new drilling effort pointed toward the same conclusion. The water wasn't isolated, it wasn't temporary, it wasn't new. It had been there far longer than any human record, sitting in quiet darkness long before continents took their current shapes. Calling it ancient isn't enough. It existed through cycles of global cooling and warming. It survived conditions that transformed every other region on Earth. Understanding how long it has been there helps explain why scientists view it with a mixture of fascination and unease. Even though Antarctica today appears like a continent frozen in place, it hasn't always been this cold. There were times in Earth's history when forests grew where ice now stands. Dinosaurs wandered through regions that now hold temperatures far below freezing. Over millions of years, tectonic plates shifted, climates changed, mountain ranges rose, and deep basins formed. Through these slow movements, Antarctica gradually drifted to its present position at the planet's southernmost point. As it settled into colder latitudes, ice began to accumulate. Snow compressed into layers. These layers thickened and hardened. Pressure increased. The weight of ice reshaped the continent itself. Eventually, the modern ice sheet took form. The ocean beneath that sheet didn't form all at once. It developed slowly as the ice thickened. Pressure increased enough to melt small pockets at the deepest layers. Geothermal heat rising from the Earth's interior kept those pockets from freezing. Over time, meltwater collected in depressions carved into the bedrock. The landscape below the ice wasn't smooth. It had ridges, troughs and valleys long before the ice arrived, much like the surface of any continent. As water filled these low points, small lakes formed. Then, as more water accumulated, the lakes began to connect. Water from higher elevations moved downward. Channels developed as water carved routes through soft sediment or followed weaknesses in the rock. These early channels expanded, creating pathways for more water to flow. The result was a developing network that would later become the hidden ocean as we know it. It wasn't an ocean in the traditional sense. It didn't have waves or shores. It didn't connect to the open sea, but it behaved like a large unified system supported by the weight of the ice above it. Every lake responded to pressure changes. Every channel shifted or expanded as water moved through it. Lakes filled and drained, some merged, some split apart. This interplay continued through countless generations of ice growth and retreat. Because Antarctica has been covered in ice for millions of years, the water beneath it has remained sealed away from sunlight and surface influences for just as long. This isolation alone makes it one of the most remarkable environments on Earth. The ocean beneath the ice developed in separation from most natural cycles. It did not freeze during periods when the surface experienced extreme cold. It did not disappear during periods of partial melting. It persisted through all of it, adapting only to the slow geological changes beneath the continent. Some lakes are believed to have remained filled for hundreds of thousands, or even millions of years. This kind of stability is extremely rare. It means the water has been part of the continent's deep time structure, not just a transient feature of modern climate. One of the best examples is a lake discovered late in the 20th century. It lies buried under nearly 4 kilometers of ice and is roughly the size of a large surface lake. Researchers studying it realised the water at the bottom had likely been liquid for an astonishingly long time. This lake wasn't unique. As mapping improved, other lakes of similar age appeared across the continent. These lakes hold layers of sediment that act like time capsules. Each layer records conditions older than any human civilization. The microbes living there evolved without sunlight or oxygen-rich environments. Instead, they survived using chemical reactions available only in isolated ecosystems like these. Their survival gives clues to conditions that might exist not just on Earth, but on frozen moons like Europa or Enceladus, where subsurface oceans have likely existed for even longer. Understanding this ancient network helps explain why scientists take it so seriously. A system that has survived for millions of years carries with it both stability and sensitivity. The stability comes from its endurance. The sensitivity comes from the fact that it developed under conditions very different from those shaping the world today. Modern climate change has added new pressures to a system built long before human activity existed. This creates unknowns that researchers are still trying to understand. The age of the hidden ocean also complicates scientific predictions about the ice sheet's behaviour. Models that simulate ice flow and melting often rely on assumptions about the structure beneath the ice. But the hidden ocean didn't develop in a straight line. It formed through cycles of growth and retreat, shaped by geology, pressure, and internal heat. Many of the routes water takes now were carved long before current ice levels formed. These old pathways may influence how water moves today, especially when pressure changes rapidly. If water begins to flow along a path carved during a much older period, it may bypass younger channels entirely. It may move faster or slower depending on the sediment left behind by ancient floods. All of these unknowns add new layers of difficulty to understanding the system. There is also evidence that the hidden ocean interacts with the coastline in ways scientists do not yet fully understand. While the water beneath the interior of the ice sheet is mostly isolated from the oceans surrounding Antarctica, some regions near the edges may allow exchanges between subglacial water and seawater. This could happen through narrow passages or deep basins that reach below sea level. If seawater enters these routes, it brings additional heat with it. Even a slight increase in temperature can accelerate melting at the base of the ice sheet. Warm seawater has played a significant role in destabilizing glaciers along parts of West Antarctica. If hidden channels allow this warm water to travel farther inland than expected, the consequences could be profound. Another important factor is the Earth's geothermal heat. The heat rising from the planet's interior has been present throughout Antarctica's history. It varies greatly across the continent. In some regions, geothermal heat is low and stable, contributing only slightly to basal melting. In others, it is significantly higher. These hotspots may have shaped the hidden ocean's earliest development. They may also be expanding it now. Measurements taken from certain areas show heat levels much higher than predicted by older models. These findings prompted researchers to reconsider how much geothermal activity influences the ice sheet. If geothermal heat has been shaping the hidden ocean for millions of years, then changes in the distribution of that heat, caused by shifts in geological activity or variations in ice thickness, could alter water flow in ways that are difficult to predict. The structure beneath Antarctica is also influenced by the remains of ancient mountain ranges. These mountains formed before Antarctica became covered in ice. Their peaks and slopes create barriers and pathways for water movement. Some lakes sit between ridges, while others rest in deep valleys carved long before the ice sheet existed. These geological features determined where the earlier subglacial lakes formed. As the ice grew thicker, water began filling these basins and connecting them. The ancient topography still controls much of the hidden ocean's shape today. But because so much of this terrain is inaccessible, scientists rely on radar and seismic surveys to infer its structure. These techniques reveal details, but never the full picture. There are always uncertainties, and those uncertainties expand when the environment being studied is millions of years old and constantly changing. Because of its age, The hidden ocean holds information about Earth's past climate. Sediments at the bottom of the subglacial lakes contain microscopic evidence of conditions that existed before the ice sheet formed. Analysing these sediments can reveal when lakes filled or drained in ancient times, how temperatures changed, what kinds of organisms lived there, and how the continent responded to different climate cycles. But retrieving these sediments requires drilling through kilometres of ice without contaminating the water below. This is a delicate task. It has been done only a few times, and each time the process requires years of planning. The samples obtained so far show layers that go far deeper into history than any surface lake could. These layers confirm that the hidden ocean has persisted through multiple ice ages, surviving environmental shifts that transformed continents and oceans across the globe. The age of the system also raises questions about its stability moving forward. A network that developed gradually over millions of years may struggle to adapt to rapid changes occurring over decades. The ice sheet above it is thinning in some areas faster than expected. As ice thins, pressure changes. When pressure changes, water pathways shift. These shifts may open new routes where none existed before. They may close older routes that maintain stability over long timescales. Researchers worry that changes in these pathways could trigger rapid ice movement. Once certain thresholds are crossed, glaciers may accelerate in ways that cannot be slowed easily. Because the system is so old, many of its behaviours are deeply ingrained in the continent's structure. Water has been following certain routes for so long that entire regions depend on the balance created by those flows. Altering one part of that balance may have consequences that spread outward, similar to how a small adjustment in one part of a machine affects all the connected components. Understanding these interactions is still an ongoing process. Each new discovery adds pieces to the puzzle, but the complete picture remains out of reach. Another factor tied to the age of the hidden ocean is the isolation of its biological life. Organisms living there have had millions of years to adapt to conditions that remain stable, only because the system is sealed from the outside world. Introducing new substances or organisms, even unintentionally, could shift that balance. This is one of the reasons scientific drilling under Antarctica is so carefully controlled. Researchers must avoid contaminating the water. They also aim to avoid altering chemical conditions that organisms have adapted to over unimaginable spans of time. These ecosystems represent some of the oldest isolated environments on Earth. Preserving them is essential both for understanding their history and for maintaining the delicate balance within the hidden ocean. The persistence of this ancient system is also part of what makes it important in discussions about global sea levels. Ice sheets respond slowly to long-term changes, but once they begin shifting, they can move faster than expected. The hidden ocean plays a large role in these shifts. As ice melts, water adds lubrication to regions that once held firm. As grounding lines retreat, more ice enters the ocean. These changes are influenced by meltwater flow, which depends on pathways carved during earlier eras. If those pathways now channel more water than they once did, or if new routes open unexpectedly, the ice sheet's behaviour could change more dramatically than models predict. For all of these reasons, understanding the hidden ocean isn't just an academic exercise, it's a way of understanding how Antarctica will respond to changes already underway. The age of the system means it carries historical patterns that shaped the continent long before humans arrived. But those patterns may no longer hold under current conditions. Studying them helps scientists identify which parts of the ice sheet are most vulnerable, which glaciers may accelerate, and how water will move as temperatures rise. Yet the more they learn, the more they realise how little is truly known. A system built across millions of years cannot be understood fully through a few decades of study. As we ease forward, the next part of this journey will begin to focus not just on the age of this hidden ocean, but on the behaviour of its moving parts. The system isn't simply ancient, it's active. Meltwater highways form without warning. Lakes drain suddenly, channels expand or collapse. Each event reveals more about how the system functions and why scientists grow more concerned with each passing discovery. This ongoing story continues to unfold beneath the quiet surface, and we can follow it step by step as it becomes clearer how water shapes the continent from below. When scientists first started mapping the water beneath Antarctica, they expected to find isolated pockets, a lake here, a small cavity there, maybe a narrow channel in a few regions where heat from the Earth's interior happened to be higher. The assumption was that these features would be scattered and mostly independent. A hidden landscape, yes, but a quiet one, something slow and predictable. That idea seemed reasonable until detailed surveys revealed something very different. Instead of small, separated features, the underside of the ice sheet held pathways far longer and more complex than anything predicted. These pathways didn't sit still. They carried water across enormous distances, carving routes that weren't supposed to exist in an environment colder and heavier than any place on the surface. When those discoveries came to light, the entire understanding of Antarctica's stability had to be reconsidered. To grasp why these meltwater highways were so unexpected, it helps to understand what the bottom of an ice sheet was once believed to look like. The traditional picture was simple: thick ice pressed against cold bedrock, forming a mostly frozen boundary except in rare areas where pressure or geothermal heat created small amounts of meltwater. In that model, any meltwater would remain local, unable to form anything resembling a long-distance river. Basic physics seem to support that assumption. Water under extreme pressure typically spreads out thinly rather than carving large passages. Freezing conditions at the base should lock it in place before it could travel far. Everything pointed to a largely static layer with only minor movement, but reality didn't match that picture. Radar measurements showed abrupt changes in ice elevation at the surface. These weren't wind effects or seasonal snowfall differences. They reflected water moving beneath the ice, filling and draining lakes through channels that must have been large enough to carry huge volumes. Satellite observations confirmed the pattern. Lakes weren't just filling and releasing small amounts of water. Some were draining billions of gallons at once. That much water needed somewhere to go. It didn't vanish. It moved, and it moved fast enough to alter the shape of the ice sheet above it. The first time researchers tracked one of these drainage events, the findings were difficult to accept. A lake in the interior of the continent emptied in a relatively short period. Not hours, but far faster than would be expected from a sealed system under intense pressure. The water didn't refreeze immediately. It carved a path downward, following terrain that had been hidden for millions of years. When the water finally reached a lower basin, the surface above that basin rose in a measurable bulge. This confirmed that water had travelled across distances thought impossible for an environment like this. The path between the lakes wasn't random. It resembled a natural conduit shaped by pressure, heat, and the structure of the bedrock below. These conduits turned out to be the first examples of the meltwater highways. They operated silently beneath thick ice, carrying water from one region to another with surprising efficiency. What made them even more confusing was the environment itself. Under extreme pressure, water should freeze at lower temperatures, but not remain fully liquid across such long distances unless something was keeping it warm enough. Geothermal heat helped in some cases, but surveys found extensive routes far from known hotspots. If heat wasn't consistent, then pressure and movement had to be playing larger roles than expected. Flowing water generates friction, and friction generates heat, which can keep channels open longer than predicted. As water moved through these paths, it warmed just enough to prevent complete freezing. That small warmth allowed it to continue travelling, creating a cycle where movement and heat reinforced one another. The channels themselves didn't behave like fixed tunnels. They changed shape depending on how much water flowed through them. If the flow increased, pressure changed. When pressure changed, ice deformed. Ice isn't as rigid as it appears. Under enough pressure, it acts like a slow-moving fluid. As water pushed against the edges of these channels, the ice above adjusted. Sometimes the channels widened. Sometimes they shifted sideways. Sometimes they collapsed and reformed a short distance away. This flexibility created a dynamic network that rewrote the idea of what could exist under the continent. Finding these moving pathways wasn't simply surprising. It created immediate concerns about the ice sheet's long-term behaviour. In regions where these meltwater highways passed under major glaciers, they acted like natural lubricants. Even thin layers of water can reduce the friction between ice and ground significantly. Large amounts of water flowing through carved channels can do even more. They allow glaciers to move faster, which sends more ice toward the ocean. That movement contributes directly to rising sea levels. The problem is not the existence of the channels themselves, but their unpredictability. Predicting how water will move through this system is extremely difficult because the channels are shaped by both the ice above and the bedrock below, and both are constantly changing. Some of the most concerning meltwater routes were found beneath glaciers already known to be unstable. In a few areas, warm ocean water had reached the grounding lines, the places where ice begins to float. This warm water carved deeper cavities under the ice. When subglacial meltwater highways connected to these cavities, they provided a direct path for inland water to reach the ocean. That connection created the potential for feedback loops. Water moving beneath the ice can thin it from below. Thinner ice lifts more easily. Lifted ice lets more warm ocean water penetrate inland. As warm water moves further in, more meltwater channels open. Each part of the loop reinforces the others, making sudden changes possible. The complexity of this network grew with each new survey. Many channels extended much farther than anyone expected. Some stretched across distances comparable to major rivers on the surface. The discovery of one long subglacial pathway revealed a route capable of moving water hundreds of kilometers from the interior toward the sea. This particular channel wasn't narrow. It had the capacity to move enough water to influence the stability of glaciers sitting above it. The fact that such a route existed in one of the coldest regions on Earth highlighted how dynamic the hidden environment truly was. Another factor that made these meltwater highways unusual was the pressure involved. Water under extreme pressure behaves differently than water in open-air rivers. It can push its way into cracks, soften sediments, and widen pathways even without large temperature changes. When water encounters beds of soft sediment, it can erode them quickly. These sediments weren't deposited yesterday. Some are remnants from eras before the ice sheet formed. As water passes through, it redistributes this material, creating new routes or altering the friction at the ice base. Changes in friction can cause glaciers to slow or speed up in unexpected ways. When a glacier speeds up, it moves more ice toward the coast. As more ice moves, grounding lines retreat. Once grounding lines retreat past certain points, they can't advance again without significant cooling. In some regions, researchers discovered that water didn't follow a single path. It branched, split, and rejoined. These branching patterns resembled drainage networks on land, but they were governed by different forces. Instead of gravity being the only driver, pressure from above, heat from below, and the structure of the bedrock influenced each fork. When a channel branched, water sometimes chose a path that appeared counterintuitive from a surface perspective. It didn't always flow downhill, it flowed toward areas of lower pressure. Pressure gradients, not elevation, became the dominant factor. Understanding these gradients is extremely difficult because they depend on constantly shifting ice thickness. If the ice above thickens or thins even slightly, the pressure changes, altering the pathways. Even more striking were the instances where lakes suddenly connected to each other without any detectable channel beforehand. A lake would release water, and that water would appear in another lake far away. This implied that the channels between them had formed recently, or had existed in a form too small to detect until flow widened them. These connections sometimes altered entire sections of the ice sheet. When water left a lake, the surface above the lake dropped. When the water arrived elsewhere, the surface there rose. These changes created subtle slopes in the ice that redirected flow patterns. The highways weren't just moving water, they were shaping the surface above them. The discovery of these large-scale pathways also forced researchers to reconsider the role of geothermal heat. The assumption had always been that meltwater highways required relatively warm conditions at the base, but many were found in regions with low geothermal readings. This suggested that friction from ice movement and the pressure-driven melting process were more powerful forces than previously understood. The combination of friction, pressure, and water movement could maintain channels even in areas where temperatures were far below freezing. The environment that allowed these highways to exist didn't need to be warm, it only needed to be in motion. This motion is one of the reasons scientists cannot easily predict which subglacial routes will grow or shrink. Movement at the base of the ice sheet is influenced by many factors working together. As ice flows, it changes the shape of the bed beneath it. As the bed changes shape, new low-pressure areas form. Water moves into those low-pressure areas. That movement widens certain paths and closes others. Meanwhile, sediment deposition continues, altering the texture of the ground. Geothermal variations add another layer. Each of these conditions interacts with the others. The result is a landscape constantly adjusting, even though the surface above appears motionless. One of the most unexpected findings came from regions where meltwater highways reached areas already known to be vulnerable due to ocean warming. When channels delivered fresh water to these regions, the buoyancy changed. Freshwater is less dense than seawater. When enough fresh water enters the ocean beneath floating ice shelves, it can lift them slightly. Lifting changes the contact between ice and rock. Reduced contact means less resistance. Less resistance means faster movement. Faster movement thins the ice further, which again allows more warm seawater to enter. Another loop forms, tied not to geothermal heat or pressure alone, but to interactions between land water and ocean water. These meltwater highways also challenge assumptions about how quickly ice sheet changes can occur. Before their discovery, many scientists believed that major changes in glacier movement would take centuries. With these highways in place, it became clear that some changes could happen over just a few decades. Water has the ability to reorganize a system faster than ice alone ever could. This does not mean that massive changes will happen overnight, but it does mean that the process may not follow the slow timeline once assumed. As more of these pathways were identified, scientific attention shifted toward understanding their potential future. The questions became less about how they formed and more about how they will behave as surface melting increases. Surface meltwater doesn't always reach the base, but in some regions it can trickle downward through cracks. If it reaches the hidden system, it adds new water to routes already carrying ancient supplies. Added water increases pressure. Increased pressure speeds flow. Faster flow widens channels. Wider channels deliver more water to vulnerable areas. This sequence could dramatically alter the distribution of water beneath the ice sheet in a relatively short time. Another important factor is that many of the meltwater highways pass beneath glaciers that drain large parts of the ice sheet. If these glaciers begin moving faster, the ice behind them will follow. Even small changes in velocity have large cumulative effects when dealing with ice measured in thousands of cubic kilometers. Areas once considered stable could begin shifting gradually until they reach a tipping point. Once that tipping point arrives, the system adjusts to a new state that may not allow a return to earlier conditions. Despite the concern these discoveries have caused, researchers often stress that understanding is still developing. The hidden environment beneath Antarctica remains one of the least accessible places on Earth. Each new measurement offers partial clarity, but also raises new questions. That's part of why these meltwater highways are so unsettling. They were never expected to exist, yet they seem to control more of the ice sheet's behaviour than many surface processes. Their ability to move water quickly across such vast distances means they can influence regions far beyond their immediate surroundings. As we move along in this journey, the next part will begin connecting these pathways to something even more surprising: what manages to survive in the dark spaces carved by these moving waters. Life that formed without sunlight, without warmth, without any of the usual conditions we rely on. Organisms that have adapted entirely to this hidden world, and their presence raises even more questions about how the environment functions and what else might be waiting under the ice. When scientists first drilled into one of Antarctica's subglacial lakes, the expectation was fairly modest. They thought they might find sterile water, perhaps a few dissolved minerals, and layers of sediment undisturbed for a long stretch of time. After all, these lakes sit under kilometres of ice, sealed away from sunlight and the surface in every meaningful sense. Temperatures hover just at or below freezing. Pressure reaches levels that would crush equipment not built specifically for the environment, and there are no plants, no sunlight-driven ecosystems, and no obvious sources of energy. Most conditions that support life elsewhere simply don't exist down here. Yet when samples were pulled up, what appeared under the microscope changed assumptions about the limits of biological survival. The water wasn't empty. It held living organisms. Not many, and not anything familiar at first glance, but alive nonetheless. This discovery surprised almost everyone involved. The immediate reaction wasn't fear or excitement, but confusion. How could anything survive here? In environments without sunlight, energy must come from somewhere else. On the surface, ecosystems usually begin with plants capturing sunlight and passing that energy up the food chain. Without that first step, ecosystems must rely on chemical energy instead. That can happen, but only in specific circumstances, such as hydrothermal vents on the ocean floor or sulfur-rich caves. Antarctica's subglacial lakes didn't appear to have those features. The water was cold, the environment was isolated, there were limited chemical sources, yet the organisms existed. When researchers looked more closely, they found microbes that survived by using chemical reactions available in the water and sediment. Instead of sunlight, these organisms used compounds like ammonia, methane, iron, or sulfur to fuel themselves. These reactions produce tiny amounts of energy compared to photosynthesis, but for microbes in extreme environments, a tiny amount is enough. What mattered wasn't the abundance of resources, but the ability to use what little existed efficiently. These microbes were specialists in survival, adapted to conditions that would kill most life instantly. Their presence suggested something important about the hidden environment. These lakes weren't temporary pools with water flowing through occasionally. They were part of a stable, long-term habitat. Stability on this scale isn't guaranteed. Water could have frozen at any point in history if pressure conditions changed. Chemical supplies could have run out, but the system persisted. Lakes filled gradually with meltwater, sediment collected from the movement of ice above. Chemical reactions continued slowly but consistently. For the microbes, that consistency was enough. The diversity of microbes was also surprising. They weren't all using the same source of energy. Some relied on nitrogen compounds. Others consumed organic materials that likely settled there millions of years ago. Some metabolized minerals from the bedrock beneath the lake. This variety meant that the hidden lake supported a network of organisms interacting with one another, even if the interactions were minimal compared to complex surface ecosystems. The lakes didn't hold large food webs, but they weren't barren either. They held life that had adapted over time to survive inside an environment defined by cold, pressure, and isolation. Sediment samples from certain lakes revealed small remnants of dead organisms, some likely carried from other regions by moving water. These remnants acted as additional sources of energy. Even when organisms died, their remains became fuel for others. Cycles that take place quickly in surface ecosystems occurred here on much longer timescales. A single piece of organic matter might be consumed, transformed, and reused by various microbes across thousands of years. Time moved differently in these ecosystems, not because time itself changed, but because the pace of every chemical interaction slowed under the cold, dark conditions. In some lakes, DNA from organisms that once lived on the surface appeared in the sediment. These weren't living creatures, but their presence revealed another piece of the puzzle. The ice sheet isn't perfectly sealed. Over long periods, small amounts of material can travel downward. Snow falling at the surface eventually becomes part of the ice layer. This ice moves slowly toward the base, carrying tiny particles along. When the ice melts at the bottom, those particles enter the water. This process helps explain how certain nutrients and materials reach the hidden lakes despite their isolation. They don't receive new supplies quickly, but they receive enough for life to continue. Another surprising discovery came from the chemical conditions within the lakes. Some lakes had oxygen dissolved in the water, even though they had been sealed from the atmosphere for millions of years. The explanation lies in the formation of the ice above. When snow accumulates at the surface, it traps air. As it compresses into ice, some of that trapped air remains in crystalline structures. When the ice melts at the base, it releases the dissolved gases into the water. This slow delivery of oxygen allowed certain microbes to survive using aerobic processes. Not much oxygen was present, but there was enough for specific organisms that required tiny amounts. Aside from lakes, meltwater channels contained small communities of organisms adapted to constant motion. These organisms didn't settle in one place. They moved as water flowed. Some clung to sediment particles, others floated freely. These communities were more sparse than those in lakes, but they still represented living ecosystems. The existence of life in these shifting routes raised questions about how organisms adapt to constant pressure changes and how they survive when their environment moves unpredictably beneath the ice. Some researchers expected that organisms in the hidden lakes might resemble microbes found in deep-sea environments, and while there were similarities, many of the Antarctic microbes showed unique adaptations. Their enzymes functioned at temperatures well below freezing. Their cell membranes remained flexible despite intense pressure. They grew extremely slowly, sometimes dividing only once every several months. These traits revealed just how flexible life can be when faced with harsh conditions. The speed of microbial activity turned out to be one of the most surprising features. On the surface, bacteria can multiply rapidly, sometimes doubling in minutes under ideal conditions. In the hidden lakes, doubling time stretched into timescales that are difficult to comprehend. A process that takes an hour for surface bacteria might take years for organisms beneath Antarctica. These slow processes meant that ecosystems developed at an almost invisible pace. Scientists studying these organisms had to adjust their expectations. If they wanted to understand how these ecosystems functioned, they needed to consider timescales far longer than those used to study typical microbial systems. Another important discovery came from the chemical compounds produced by these organisms. Some microbes created byproducts that influenced the chemistry of the entire lake. For instance, bacteria consuming iron or sulfur compounds produced new chemicals that could then be used by other organisms. This created a layered system of energy exchange. Even though these exchanges happened slowly, they created a structured community where each group contributed to the overall stability of the environment. These interactions were so subtle that early studies missed them entirely. Only detailed chemical analysis revealed the complexity beneath the surface. The organisms living here also gave scientists a better understanding of how life might exist elsewhere in the universe. If microbes can survive in dark, cold, pressurized environments beneath Earth's ice, then similar forms of life might exist on icy worlds like Europa or Enceladus. These worlds have subsurface oceans far larger than Antarctica's, and they likely have chemical energy sources similar to those found in Antarctica's lakes. While this idea doesn't prove anything about extraterrestrial life, it provides a compelling example of how environments that seem inhospitable to us can support life adapted to entirely different conditions. Another unexpected implication involves how organisms might influence ice sheet behavior. Microbial activity in these lakes can affect sediment stability. Certain microbes produce substances that bind sediment particles together. Others break down minerals that help keep sediment compact. These processes occur slowly, but over long periods, they can change how sediment behaves under pressure. Sediment stability influences how water moves, which influences how ice moves. This means that microbes, in their own indirect way, may play a role in shaping the hidden world beneath Antarctica. Some lakes also contained thin mats of microbial material forming on the sediment surface. These mats were fragile and easily disrupted, but their presence indicated that organisms were not merely drifting passively. They were forming structures, however small, that helped them remain in place. These mats may have existed for thousands of years, growing only millimeters in that time, but even that minimal growth showed that these organisms adapted to remain stable in environments where everything else was moving. The discovery of viruses in these lakes added another layer of complexity. These viruses didn't resemble the harmful viruses people usually think about. They targeted bacteria, influencing microbial populations. In stable ecosystems, viruses help regulate the balance between different microbial groups. They prevent any single type from dominating. Their presence in Antarctica's lakes suggested that even here, in one of the harshest environments on Earth, ecosystems maintained balance through interactions similar to those found in more familiar settings. These viruses also evolved slowly, adapting to microbial hosts that reproduced at incredibly slow rates. Understanding them required patience because the changes researchers looked for didn't happen quickly. The biological discoveries beneath the ice also influenced how drilling operations were conducted. When early drilling projects risked contaminating the environment, strict guidelines were established to prevent introducing surface organisms into the lakes. Contamination could disrupt ecosystems that had developed over millions of years. To avoid this, scientists designed sterile drilling methods that used clean water and equipment carefully monitored for impurities. These precautions highlighted just how fragile the hidden ecosystems were, despite their long survival. The knowledge gained from studying these organisms changed how scientists viewed Antarctica's hidden ocean. It was no longer seen as just a geological or hydrological system. It was also a biological one. Life contributed to chemical cycles, influenced sediment movement, and helped stabilize or alter certain aspects of the environment. The water wasn't simply flowing beneath the ice. It was hosting communities, each shaped by extreme conditions and long isolation. Another interesting aspect of these ecosystems is how they respond to sudden changes. When a lake drains rapidly through a meltwater highway, the organisms within it move with the water. They might be carried into a new basin or into a channel where conditions are slightly different. The sudden change in pressure, temperature, or chemistry could affect their survival. Yet many seem to persist despite these shifts. Their ability to tolerate abrupt environmental changes suggests that while they are adapted to stable conditions, they are also flexible enough to cope with disturbances. This adaptability makes them important subjects for understanding resilience in extreme ecosystems. The presence of these organisms also raises questions about the age of the hidden ecosystems. Did life begin there after the lakes formed, or did life migrate downward from the surface long ago? Some DNA evidence suggests that certain microbial lineages may have ancient origins, possibly predating the formation of the ice sheet. Others appear to be adapted descendants of surface organisms transported downward by slow ice movement. Understanding this history requires more sampling, more drilling, and more analysis, but every indication so far points to a long and complex story of biological persistence. These organisms also highlight how little is known about the deeper regions of the hidden ocean. Most lakes have not been sampled, and the channels connecting them remain largely unexplored. There may be ecosystems far different from those already studied. There may be organisms adapted to conditions even more extreme. There may be interactions taking place that haven't yet been imagined. Every sample taken from these environments has revealed something unexpected, suggesting that much more remains hidden. As we move further into this story, the next part begins focusing on an aspect that concerns scientists beyond biology. The hidden lakes and meltwater highways interact with pockets of warmth that should not appear in such a cold place. These warm regions change how ice melts, how water flows, and how the entire system behaves. Understanding why warmth appears where it does, and what it means for the stability of the ice sheet, is another essential step in understanding the hidden world beneath Antarctica. When people look at Antarctica from the outside, the last thing they expect to hear is that warmth plays a major role in shaping the continent. The entire region appears to be the definition of cold. It has months without sunlight, temperatures that fall well below anything comfortable, and winds strong enough to erase any sign of movement. Yet underneath all of that sits a world where heat, subtle as it may be, determines how water moves, how ice shifts, and how stable the entire system remains. This warmth doesn't come from the sun. It doesn't arrive through seasonal changes. Instead, it rises from below, from inside the Earth itself. And although it may not seem like a significant amount of heat compared to the scale of the ice sheet above, it is powerful enough to create meltwater highways, open lakes, and pockets of activity that scientists never expected to find. To understand why this warmth matters so much, it helps to picture the base of the ice sheet as a place where weight alone changes the behaviour of everything it touches. Ice kilometres thick presses downward with enormous force. That pressure lowers the melting point of ice, meaning it can turn into water even when temperatures remain well below freezing. But pressure alone doesn't explain all the meltwater present beneath Antarctica. There must be an additional source of heat. That source is geothermal energy. It rises from the planet's interior and has been doing so since long before Antarctica drifted to the bottom of the world. Geothermal heat is not evenly distributed beneath Antarctica. Some regions release only small amounts of warmth, barely enough to influence melting. Others produce significantly more. This uneven distribution is the result of deep geological structures, including old volcanic systems, thin sections of crust, and areas of residual activity left from ancient tectonic movements. When researchers first measured geothermal heat beneath the continent, they expected low readings across most regions. The reality proved far more complicated. In certain locations, geothermal heat levels were high enough to keep subglacial lakes from freezing, even under intense pressure. Some areas showed heat fluxes similar to regions known for volcanic activity, despite having no visible surface volcanoes. These measurements were unexpected because the presence of such heat means the underside of the ice sheet is far more dynamic than previously assumed. Heat rising from below can melt ice continuously, feeding lakes that have remained liquid for millions of years. It can also help maintain the long subglacial channels that allow water to travel across vast distances. One of the most unexpected findings came from a region in East Antarctica. The ice above this area was believed to be some of the coldest and most stable on the continent, but radar and seismic measurements revealed pockets of warmth beneath it that didn't match the surface conditions at all. These warm areas were strong enough to create persistent lakes under the ice, some as large as major urban lakes that sit in temperate climates. The mere existence of these lakes challenged the assumption that the interior of Antarctica was a fully frozen, unchanging block. Another region showed heat levels so high that they hinted at volcanic activity deep below. This doesn't mean magma is pushing toward the surface, but it does mean the crust in that area is thinner than expected, or that remnants of an ancient volcanic system still generate enough heat to affect the environment. When the ice above these regions melts from below, it creates water that may move into surrounding basins, forming part of the broader meltwater network. These warm pockets act like engines in a hidden machine. They don't drive the entire system, but they influence how parts of it function. The existence of geothermal hotspots doesn't mean that Antarctica is warming from below in a sudden or dramatic way. These sources of heat have likely been present for millions of years. The concern is not their presence, but how they interact with the modern climate system. As temperatures warm at the surface, ice thins in some regions. Thinner ice changes the amount of pressure at the base. When pressure changes, the melting point changes. Combined with geothermal heat, this can lead to increased melting even in areas once considered stable. A small change in one part of the system can ripple through the entire network of lakes and channels. Another factor influenced by geothermal heat is the movement of entire glaciers. When warm pockets sit beneath major glaciers, the ice becomes more prone to sliding. Water acts as a lubricant, reducing the friction between ice and rock. Even a small increase in basal melting can change how fast a glacier moves. When a glacier gains speed, it pushes more ice toward the ocean. This movement may not seem dramatic at first, but over time it can reshape coastlines. In some cases, glaciers that remained stable for thousands of years can begin moving faster within decades once melting increases. One example comes from a glacier in West Antarctica known for its vulnerability. Measurements show that geothermal heat beneath it was significantly higher than expected. Combined with warm ocean water at its grounding line, this heat helped create a situation where the glacier became one of the fastest changing regions on the continent. Water melted at the base flows into the hidden network, creating conditions that accelerate ice loss. The glacier sits in a deep basin that slopes downward inland, making it even more sensitive to changes in basal melting. Once warm water reaches certain depths, retreat becomes difficult to stop. Another area of concern involves regions where geothermal heat has created deep cavities under the ice. These cavities can fill with meltwater and expand over time. When they grow large enough, they may cause sections of the ice above them to shift or collapse. Even if the collapse is not sudden on human timescales, the redistribution of weight can redirect water flow, opening new pathways or closing others. Each change alters the behavior of the ice sheet, making predictions more challenging. Some scientists have described these warm zones as weak points beneath the ice. Not weak in the sense of structural failure, but weak because they introduce variability. A stable environment is easier to understand and predict. One with pockets of warmth scattered unpredictably beneath kilometers of ice behaves more like a complex system where small changes can grow into larger effects. The warmth doesn't need to be dramatic. It merely needs to be enough to alter the balance between ice and water. Another important aspect of geothermal heat is how it interacts with sediment beneath the ice. In some areas, sediment acts like a sponge, trapping heat and releasing it slowly. In others, sediment consists of soft, unconsolidated material that melts easily when exposed to warmth. These differences can influence water flow. Water moving over hard rock behaves differently from water moving over soft sediment. The presence of warm zones can soften sediment to the point where it becomes easier for water to carve through it. This allows channels to expand, connecting lakes in ways that weren't possible before. In certain regions, geothermal heat also interacts with old volcanic structures buried deep below the ice. These structures may not be active in the traditional sense, but their residual heat affects local melting. Some have been detected through magnetic anomalies and seismic readings. These hidden features create warmer zones that help sustain the meltwater system. Their influence is subtle, but significant. Without them, some subglacial lakes might never have formed. Another surprising finding related to geothermal heat is its connection to the speed at which ice changes thickness. As warm pockets melt the base of the ice, the weight distribution above shifts. This can lead to changes in ice flow that are not always intuitive. In some cases, melting at the base causes the ice above to thin more quickly. In others, it leads to localized thickening because ice flows differently when basal conditions change. These interactions are so complex that researchers often describe them as puzzles, formed by layers that are constantly moving. One area where geothermal heat seems especially influential lies beneath the East Antarctic ice sheet. Long believed to be stable, portions of this region show signs of dynamic behavior linked to basal melting. Even slight increases in geothermal activity could alter water pathways under this massive section of ice. Although East Antarctica is still generally considered less vulnerable than West Antarctica, the discovery of widespread warmth beneath its base suggests that some areas may be more sensitive than previously thought. Another key point is that geothermal heat does not exist in isolation. It interacts with pressure, friction, surface temperature changes, and ocean conditions. When all these factors operate together, they create scenarios where ice behaves differently than expected. For example, friction from ice movement generates additional heat. When ice flows over rock, the friction can warm the base enough to contribute to melting. In regions where geothermal heat is already present, friction adds to the total energy available for melting, pushing the system even further from previous assumptions. What makes this warmth especially concerning is not its strength but its placement. It appears in regions where stability depends on the ice remaining grounded and cold. If warm pockets form beneath ice shelves or grounding lines, melting can proceed from below while surface conditions appear unchanged. This hidden erosion weakens the connection between ice and land. Once ice begins lifting from the bedrock, water can rush underneath in larger volumes, accelerating the detachment process. Another complication arises from the interaction between geothermal heat and meltwater pressure. As water fills cavities created by warmth, it increases pressure at the base. Higher pressure can force water into new areas, widening cracks or pushing meltwater through sediment. This redistribution of water changes the internal balance of the ice sheet. In some cases, it may create new routes for warm ocean water to enter. In others, it may destabilize parts of the ice sheet by reducing friction at critical points. Researchers studying these warm regions understand that even slight changes in geothermal output could have significant consequences. Although geothermal heat typically changes slowly over geological timescales, its interaction with modern climate warming can amplify the effects. Surface melting introduces new water into a system already shaped by warmth from below. The combination of water from above and heat from below increases the likelihood that meltwater highways will expand or that new lakes will form. Despite all of these concerns, geothermal heat also provides valuable insight into the continent's deep history. By studying the distribution of warmth beneath the ice, scientists can learn about Antarctica's geological past. Areas with higher heat flow may point to ancient volcanic activity or crustal thinning. Other regions might indicate tectonic shifts that occurred long before humans arrived. This information helps researchers reconstruct how the continent formed and how the hidden environment beneath the ice evolved. The presence of warmth under Antarctica also underscores how interconnected the environment is. Even in a region dominated by cold, small amounts of heat shape the entire system. Warmth determines where water forms, how it moves, and where it accumulates. It influences glacier speed, ice shelf stability, and the structure of the hidden landscape. Without it, the subglacial environment would look entirely different. Many lakes would not exist. Meltwater highways might never have formed. The ice sheet's movement would be slower and more predictable. Instead, warmth moves quietly beneath the ice, reshaping the world above it in subtle ways. Not dramatic, not loud, but steady enough to matter. And it is this steady influence that brings scientists back to the same concern. If warmth can create such complex effects over long periods, then changes happening now at both the surface and the coast may combine with that basal heat to produce outcomes that older models never accounted for. As we continue this slow journey, the next part brings us into the spaces where pockets of water grow into enormous cavities, sometimes large enough to compare with structures on the surface. These caverns sit beneath the ice, shaped by warmth, pressure, and movement. They exist in places where nobody expected empty space to form at all, and their presence adds yet another layer to the growing understanding of Antarctica's hidden world. When scientists first began seeing signs of enormous voids beneath Antarctica's ice sheet, they hesitated to accept the idea. Cavities on that scale didn't fit earlier models of how ice should behave. The base of an ice sheet, according to long-standing assumptions, should be compressed tightly against the ground, except where small pockets of meltwater created thin layers of separation. Everything was supposed to be dense, heavy, and pressed firmly into place. Space wasn't expected, certainly not vast open areas beneath ice thick enough to dwarf mountains. but as measurements improved, the signals became clearer. There were places under the continent where the ice wasn't sitting on rock or sediment. It was suspended above air and water-filled caverns, some reaching sizes that startled even the teams most familiar with Antarctica's complexities. The first of these discoveries came from radar surveys mapping glacier stability along parts of West Antarctica. Researchers saw reflections that didn't match anything typical. Instead of showing solid contact at the base, the reflections revealed open spaces. At first, these were brushed off as possible errors, but repeated measurements told the same story. Something had carved out massive rooms under the ice. When the initial dimensions were estimated, the numbers didn't seem believable. The cavity beneath one glacier was roughly tall enough to hold a skyscraper and large enough in volume to rival city districts. And it wasn't a single anomaly. Similar features later began appearing in data from various parts of the continent. Some were smaller, some were even larger. All challenged the idea of a simple, stable boundary between ice and the landscape below. The formation of these caverns comes down to a combination of water flow, heat, and pressure. These forces acted together over long periods, gradually eroding ice from beneath and creating pockets that expanded slowly. The water flowing through these areas gained warmth from geothermal heat or friction from moving ice. As it flowed against the underside of the ice sheet, it melted more ice, which added to the water already present. This ongoing cycle gradually removed layers from the base. The cavities didn't appear overnight. They grew through subtle, consistent melting that spread outward until entire regions of the ice were lifted from the bedrock below. One of the most significant factors in creating these caverns is the grounding line, where ice transitions from resting on land to floating on the ocean. In regions where the grounding line retreats due to melting, seawater can push farther inland. Warmer ocean water carries enough energy to melt ice much faster than meltwater alone. When this water reaches areas below glaciers, it hollows out the base, carving deep, open spaces that expand as long as warm water continues flowing into them. These cavities affect how the ice above behaves. When a portion of the ice loses its connection to the bedrock, it becomes more fragile. It may lift upward or shift slightly. These changes influence cracks, fractures, and the distribution of weight across the glacier. Even small shift can alter the glacier's speed, pushing more ice outward and causing further retreat of the grounding line. One of the largest known sub-ice cavities was discovered under a glacier already considered highly unstable. The cavity measured roughly 1 kilometre tall in places and extended across an area large enough to surprise even seasoned researchers. This enormous space formed because warm ocean water entered the region repeatedly, melting ice from below at a rate far higher than predicted. Models had estimated 1 melting rate. Reality revealed something several times faster. What concerned scientists most wasn't just the size of the cavity, but how quickly it formed. Most of the melting that created it happened within a handful of years. For a structure that large to appear in such a short time, shows how rapid change can be once conditions shift toward instability. But not all caverns result from ocean water. Some form deep within the interior of Antarctica, far from any coastline, where the ice is thickest and outwardly quiet. These interior caverns result from a long build-up of meltwater that begins to pool and expand beneath certain layers. Meltwater highways deliver water to basins where it collects and exerts upward pressure. When enough water gathers, it pushes the ice upward slightly, creating a gap between ice and ground. Over years or centuries, water continues to gather, slowly enlarging the gap. Eventually, the cavity becomes large enough to hold enormous volumes of water and air. These interior caverns behave differently from those carved by ocean water. They expand slowly but steadily, weakening the ice above by reducing contact with the underlying terrain. The presence of air inside these caverns raised additional questions. Air shouldn't easily accumulate in such deep, pressurized environments. Yet some caverns appear to hold both water and air pockets. The most likely explanation is that as water melts ice above it, it releases small amounts of dissolved gases trapped in the ice. Over time, these gases accumulate, forming thin layers of air. While the air doesn't form large empty chambers, it can create pockets that further separate ice from rock. Even a small amount of air can reduce friction drastically, smoothing the way for the ice to slide. Another reason these caverns are concerning is their influence on how the ice fractures. Ice sitting over a cavity lacks full support. It may sag slightly. This sagging can create cracks or widen existing fractures. Some fractures eventually reach the surface. When this happens, meltwater from above can pour into the fractures and travel downward. If it reaches the cavity, it adds more water to a system already under pressure. Additional water increases the size of the cavity or opens new routes. This cycle continues, making the ice above more prone to breaking or accelerating. One of the most subtle effects of large caverns is how they alter stress patterns across the ice sheet. Even if the surface doesn't crack, the internal stress changes. Ice behaves differently when supported unevenly. Areas above cavities may move faster, while areas on either side move more slowly. This differential motion can twist, warp, or distort the ice. Over long timescales, this distortion can contribute to glacier instability. Surface observations alone cannot predict how the ice will behave without understanding what lies beneath it. Caverns introduce uncertainties into any model attempting to simulate future ice behavior. Using radar to detect these caverns is challenging. Ice scatters radar signals, especially when the ice is thick or contains mixed crystals. Caverns also change shape over time, which complicates interpretation. In some cases, the first sign of a cavern isn't a direct radar reflection, but a change in ice elevation on the surface. When ice thins over a cavity, the surface may sink slightly. When the cavity fills with water, the surface might rise. These changes are small but detectable with modern satellite tools. Tracking them over time revealed the presence of cavities growing beneath areas once assumed to be stable. Researchers have noted that caverns beneath glaciers behave similarly to gaps under bridges. A bridge's stability depends on its support points. Remove one support, and the entire structure becomes vulnerable. For glaciers, the bedrock acts like the supports. Caverns remove portions of that support. As a result, glaciers can become more susceptible to rapid changes. Ice may sag, crack, or accelerate. Some glaciers that show rapid acceleration today may owe part of their instability to the presence of caverns that formed silently over long periods before being detected. Another important feature of these caverns is the mixing of water within them. Water from meltwater highways, geothermal melting, and ocean intrusions can gather in the same cavity. When these different water sources mix, their combined heat can accelerate melting even more. Warm water rises to the top of the cavity and melts the underside of the ice. As that water cools, it sinks, picking up additional heat from geothermal sources or friction. This circulation continues, maintaining a steady melt rate. Caverns with active water circulation can expand much faster than those without significant movement. Some caverns also contain sediment layers that fell from ice above. These sediments hide clues about past melting events. By studying them, researchers can piece together a timeline of how long a cavity has existed and how quickly it expanded. In some cases, sediment layers revealed that cavities persisted for thousands of years. In others, the layers showed rapid changes within only a few decades. This variation demonstrates how unpredictable the system can be. Caverns aren't uniform. They don't grow at consistent rates. They respond to a combination of water supply, heat, pressure, and ice movement. Even small shifts in one factor can trigger noticeable changes in cavity growth. Some of the most surprising caverns have been found beneath floating ice shelves. These shelves extend from the continent into the ocean, where they float on seawater. Warm ocean currents can carve large cavities beneath them, thinning the ice from below. One cavity beneath a large ice shelf grew so quickly that its size shocked even experienced glaciologists. The cavity expanded upward, thinning the ice dramatically over a short period. This thinning weakened the ice shelf, making it more susceptible to cracking. If an ice shelf breaks apart, the glaciers feeding into it accelerate, delivering more ice to the ocean. In this way, a cavern may indirectly contribute to rising sea levels. Floating ice shelves behave differently from grounded glaciers, but caverns affect both. Under floating shelves, cavities allow water to travel farther inland, carrying heat that melts even more ice. Under grounded ice, caverns remove support and destabilize ice flow. In both cases, caverns represent hidden vulnerabilities that surface observations cannot detect. The scale of these caverns also forces scientists to reconsider how quickly change can occur. Earlier models predicted that large structural changes within the ice sheet would take centuries, but the presence of massive cavities forming in only a few decades challenges that idea. The ice sheet is more sensitive to internal changes than once believed. Caverns don't need to collapse in dramatic ways to cause problems. Their gradual expansion is enough to weaken the ice and redirect water flows. One of the most complex aspects of these caverns is predicting their future. They may continue expanding. They may drain in sudden events. They may connect to other cavities or lakes. Each outcome affects the system in different ways. A drained cavity could cause ice to settle suddenly. A growing cavity could allow more warm water to spread. A newly connected cavity could create long-distance water pathways that bypass earlier routes. All of these changes influence glacier movement, meltwater distribution, and the overall stability of the ice sheet. Despite their size, these caverns remain difficult to study directly. Drilling into them is risky. Introducing equipment might destabilize the delicate balance of water and ice inside. Even sending instruments down through drilled holes can create pathways for water to rise or escape. As a result, most information about these caverns comes from indirect observations, satellite data, radar reflections, seismic readings, and computer modelling. Yet every piece of evidence confirms the same central point. The underside of Antarctica is not a flat, uniform plain. It is a varied, evolving landscape shaped by forces that don't operate anywhere else on Earth. Caverns the size of city blocks, skyscrapers, or even small urban centres lie hidden under ice that looks deceptively solid from the surface. Their existence is a reminder that the appearance of stillness in Antarctica masks an environment full of shifting structures and complex interactions. As we move deeper into this exploration, the next part will follow the oldest inhabitants of this environment, not the organisms themselves, but something even more resilient. Microbes that have endured in places where almost nothing else can survive, holding on to survival in conditions unimaginably remote from the surface world. Their persistence raises questions about what life can endure and how long it can last under pressure and cold that never lets up. When scientists first realised that Antarctica's hidden lakes were not sterile, the discovery caused a quiet shift in how people understood extreme environments. Finding life in a place sealed off from sunlight for millions of years didn't just stretch expectations, it pushed scientists to rethink what it means for life to persist. If microbes could endure in lakes buried under kilometres of ice, fed only by slow chemical reactions and ancient minerals, then the boundaries of habitability were wider than anyone had assumed. It wasn't only that life had survived, it was how long it had been doing so, and how little the environment had changed during that time. This combination of isolation, age and resilience made these organisms some of the most intriguing on Earth. What caught scientists by surprise wasn't just the presence of microbes, but their diversity. These weren't identical cells all copying the same survival strategy. They represented a wide range of metabolic approaches. Some relied on reactions involving sulfur compounds, others used iron, others consumed small traces of organic carbon locked in the sediment. Each microbe had adapted to a different niche within the harsh environment. These niches were small and limited, yet they formed a stable system that persisted long after similar ecosystems elsewhere disappeared. Even in tiny amounts, the energy available at the base of the ice sheet sustained a complex web of microbial interactions. These organisms lived in conditions defined by extremes. The lakes were pitch black. Temperatures hovered just above freezing due to a delicate balance of pressure, geothermal heat, and the insulating effect of thick ice. Oxygen existed only in tiny amounts. Nutrients entered slowly through the breakdown of ancient sediments, or through the melting of ice that carried trapped gases and particles. The pressure was intense, much higher than the surface of the ocean. Despite all of this, the microbes didn't simply exist. They functioned, they reproduced, although at extremely slow rates. They interacted with their environment in ways that influenced the chemistry of the water and sediment. Some samples revealed microbes that metabolized iron in forms that shouldn't be accessible in such low-energy environments. These processes occurred at rates so slow that they were difficult to measure, but the microbes persisted nonetheless. Their enzymes adapted to cold temperatures. Their membranes remained workable under pressure. Everything about their biology suggested a long history of fine-tuning to one of the harshest stable environments on Earth. It wasn't only bacteria that caught attention. Viruses, which infect and regulate bacterial populations, were also found. Their presence meant that even in these isolated lakes, microbial communities followed familiar ecological dynamics. Viruses helped control which microbes dominated. They influenced nutrient cycling by breaking open bacterial cells, which released compounds that other microbes could use. This cycle, though slow, added complexity to an environment that initially seemed too extreme to support lasting biological networks. Some lakes showed evidence that their microbial populations dated back hundreds of thousands of years. Others held clues to survival dating back far longer. One of the most important implications was that these organisms had persisted through multiple glacial cycles. The ice sheet had grown and thinned repeatedly over millions of years, yet the lakes remained liquid and the microbes endured. Their ability to survive long-term isolation sets them apart from most known life on Earth. Scientists studying these microbes often describe them as living in slow motion. Their metabolic rates are among the lowest ever recorded. Many of their processes take hundreds or thousands of times longer than similar processes in typical bacteria. A single cell division might take months or even years. Yet despite this slow pace, their communities remain stable. Life doesn't always require speed. It requires consistency. And the hidden ocean beneath Antarctica provides that consistency, even if it is defined by cold, darkness, and pressure. The sediment beneath these lakes contains layers that reveal the history of the environment. Microbial activity changes the chemical composition of sediment over time. By analysing these layers, scientists can determine when lakes filled or drained, how nutrient levels shifted, and which metabolic pathways dominated in different eras. Some layers show evidence of microbial communities that existed long before the current ice sheet formed. Others reveal shifts in metabolism that correspond with subtle changes in water flow or chemical availability. Each layer acts like a record of life deep beneath the ice, extending far beyond human timescales. One of the most intriguing aspects of these microbes is how they persist even when energy sources are extremely limited. Many surface organisms require relatively constant supplies of nutrients and energy to survive. These ancient microbes do not. Their survival strategies involve reducing activity to minimal levels. They maintain only the processes required to stay alive. Everything else is slowed. Their cells remain intact for years without dividing. Their metabolic reactions operate near the edge of detectability. This ability to enter states of prolonged survival without significant energy input allows them to withstand conditions that would be lethal to most forms of life. Some microbes found beneath the ice rely on processes that appear similar to those seen in deep ocean vents, but without the heat normally associated with such environments. Instead of using chemical energy from hot fluids, they rely on minerals present in the sediment or on gases trapped within the ice. They carry out reactions at temperatures near freezing, adjusting their internal chemistry to function in a setting where reaction rates are naturally slow. Their adaptations include enzymes that remain flexible at low temperatures and cell structures designed to withstand crushing pressure. These traits offer insights into biochemical resilience and could help explain how life might exist on other worlds where similar conditions prevail. Another important discovery involved microbes that produce compounds capable of affecting the physical environment. Some create substances that bind sediment particles together, subtly altering the stability of the lake bed. Others release compounds that help dissolve certain minerals, which then release nutrients that other microbes can use. These processes occur slowly, but over long timescales, they shape the chemistry of the lakes. In this way, the microbes contribute to a self-sustaining cycle. They don't simply survive within the environment, they help create the conditions that allow survival to continue. When scientists considered how these organisms might have arrived in the lakes, several possibilities emerged. They might have migrated downward as the ice formed millions of years ago. Snow falling at the surface can trap microbes. Over long periods, this snow becomes part of the ice sheet. As the ice flows and reaches the base, meltwater releases these trapped organisms into the lakes below. This could explain the presence of certain lineages similar to surface microbes, but not all lineages fit this description. Some appear far older and less related to surface life. These might represent ancient communities that were already thriving in sediment before the ice advanced. If so, they survived the transition from a once temperate environment to the frozen one that exists today. The isolation of these ecosystems raises questions about evolution in extreme environments. Without sunlight or complex food webs, natural selection operates differently. Changes in microbial populations take much longer. Mutations accumulate slowly because cell divisions are infrequent. As a result, some of these microbial lineages may closely resemble ancient forms of life. They offer a window into biological processes that might have been common on early Earth before the atmosphere and climate stabilized. Another aspect that makes these organisms remarkable is their response to changes in water movement. When lakes drain or fill, pressure and chemical conditions shift. These changes can stress microbial communities, yet many seem adapted to handle such variations. Their slow metabolism allows them to remain stable even when water chemistry changes. They don't require immediate adjustments. Instead, they endure until conditions settle again. This resilience helps explain how they survive in a system that experiences occasional turbulence despite being isolated from surface weather. The presence of these organisms also has implications for how scientists study other extreme environments. If microbes can survive in Antarctica's hidden lakes, they might also survive in deep crustal rocks, frozen desert soils, or other remote places on Earth that receive little attention. Similar habitats exist in places where surface conditions appear inhospitable, but where isolated pockets of stability exist underground. The persistence of these microbes suggests that life might be more widespread than earlier assumptions allowed. These findings also deepen interest in icy moons orbiting other planets. Moons like Europa and Enceladus have subsurface oceans beneath thick ice. If Earth hosts ecosystems beneath its own ice sheet, it becomes easier to imagine similar ecosystems existing elsewhere. Of course, this doesn't confirm anything about extraterrestrial life, but it provides a relevant example. Life doesn't require sunlight. It requires energy, stability, and the ability to adapt. The microbes beneath Antarctica demonstrate how minimal those requirements can be. Drilling into these lakes to collect microbial samples requires incredible caution. Introducing surface contaminants could disrupt ecosystems that have existed undisturbed for millions of years. Scientists use sterilized equipment and carefully filtered water to minimize risk. These precautions highlight how delicate and unique the environment is. A microbial community that has remained stable through countless climate cycles could be thrown off balance by the introduction of new organisms. Protecting these ecosystems ensures that future generations can study them in their natural state. One of the most fascinating aspects of these ancient microbes is that their survival influences the environment in small but measurable ways. They alter chemical gradients, affect sediment texture, and in certain lakes may contribute to the formation of specific minerals. These interactions occur slowly, but across long time spans they shape the environment in ways that help maintain habitability. They are part of a feedback system that stabilizes the hidden lakes even as pressures and flows change above them. Some lakes show evidence of long periods during which microbial populations increased slightly, only to decrease again as nutrient levels changed. These fluctuations likely correspond to slow changes in lake structure or shifts in meltwater input. Even though the lakes seem isolated, they are not static systems. They evolve gradually, and the microbes evolve along with them. Tracing these changes helps researchers understand how ecosystems respond to long-term environmental shifts. Another interesting feature of these organisms is their genetic adaptability. Although they evolve slowly, their genomes show signs of modifications that help them survive low-energy conditions. Many have genes that regulate stress responses efficiently. Others possess mechanisms to repair DNA damaged by environmental factors. Because they live under pressure, they must maintain structural integrity in conditions that constantly threaten to destabilize proteins and membranes. Their adaptations illustrate how life can maintain function even in environments that stress every biochemical process. The persistence of these microbes also raises questions about long-term planetary stability. A system that supports life over millions of years without surface input demonstrates resilience. Though the environment is harsh, it remains relatively consistent over geological timescales. This consistency allows life to adapt deeply and thoroughly. It suggests that if similar environments exist elsewhere in the solar system, they too might support long-lived ecosystems. Another factor that interests scientists is how these microbes might respond if environmental changes at the ice surface accelerate. As ice melts more rapidly in certain regions, pathways for meltwater could shift. New channels might introduce water from previously disconnected lakes. Changes in pressure might alter chemical balances. These adjustments could affect microbial populations, either expanding them or reducing them depending on the changes. Understanding how they respond provides insight into how resilient ecosystems manage disruption. Despite their resilience, these communities also face limitations. They can survive with extremely low energy, but there are thresholds below which survival becomes impossible. If a lake freezes entirely or if chemical sources are depleted, the microbes may not endure. Scientists remain uncertain how close some lakes are to these limits. In certain regions, the balance between melting and freezing is delicate. Small changes could push ecosystems into conditions beyond their ability to cope. Studying these limits helps researchers understand the boundaries of habitability in extreme environments. Even with all these discoveries, most of Antarctica's hidden lakes remain unexplored. Only a handful have been sampled directly. The organisms found so far likely represent only a fraction of what exists beneath the ice. New approaches to remote sensing and chemical analysis may eventually reveal more, but drilling into every lake is neither practical nor desirable. The environment is too delicate. As a result, much of the hidden microbial world will remain out of reach, known only through indirect evidence and the occasional sample retrieved after years of planning. What is clear is that the oldest inhabitants of Antarctica's hidden ocean are not passive remnants of ancient life. They are active participants in the environment. Their slow, steady metabolism shapes chemical gradients. Their presence reveals the long evolutionary history of isolated ecosystems. They demonstrate that life can endure in places where energy is minimal and conditions remain nearly constant for millions of years. As this long journey beneath the ice continues, the next part will shift attention from life itself to the fragile balance that controls the ice sheet above. The presence of water and warmth influences how ice holds together. Some portions of the ice behave like solid bedrock, while others rest precariously on the edge of instability. Understanding how these structural weaknesses form and what they mean for the future is essential for grasping why scientists worry about certain regions more than others. When scientists talk about Antarctica's ice shelves, they often describe them as the continent's protective barrier. These shelves form where thick, grounded glaciers move far enough toward the ocean that they begin to float. Once afloat, they spread outward into long platforms of ice that can extend hundreds of kilometres over the water. From above, they look like stable extensions of the continent. They appear solid, unmoving and dependable. But the truth beneath that appearance is more complicated. Ice shelves act as supports that slow the flow of glaciers feeding into them. Remove or weaken a shelf, and the glaciers behind it accelerate. For years, many shelves seemed stable enough that worry remained low. Then new observations revealed that some shelves were changing faster than expected, thinning in ways that didn't match older predictions and shifting in patterns scientists hadn't anticipated. Understanding what makes an ice shelf stable begins with understanding how it connects to the land beneath it. A shelf floats on seawater, but parts of its underside still rest on features like underwater ridges or shallow regions of the ocean floor. These contact points act like anchors. They hold portions of the shelf in place and slow the movement of ice behind them. When these grounding points weaken or melt, the shelf loses stability. Even a small shift can change how force is distributed across the entire structure. Once force distribution changes, cracks can grow, channels can widen, and stress can concentrate in places that were previously secure. Another factor influencing ice shelf stability is the temperature of the water beneath them. Many ice shelves float over water much warmer than the freezing temperatures at the surface. This doesn't mean tropical warmth. It means water that is only a few degrees above freezing, but still warm enough to melt ice efficiently. Warm water circulates beneath ice shelves along patterns shaped by ocean currents. Some of this water is brought from deeper parts of the ocean. Some arrives from regional circulation caused by wind changes. When this warmer water meets the underside of an ice shelf, it can carve deep cavities. These cavities are often much larger than expected. Over time, they thin the ice enough to weaken its overall structure. Scientists studying this melting pattern noticed something unsettling. Thinning wasn't happening evenly. Some sections of an ice shelf might lose ice rapidly from below, while nearby sections remained almost unchanged. This uneven thinning created stress. Ice shelves flex slightly as they move, and uneven thinning causes them to flex more in some places than others. Increased flexing leads to cracks. These cracks can stay small for years, but if conditions continue, they expand. Many shelves contain networks of cracks visible on satellite images. Some cracks remain stable, widening only slightly each year. Others grow quickly once the ice shelf thins past a certain point. In parts of West Antarctica, one particular ice shelf received attention because its thinning progressed faster than earlier data suggested. Measurements showed that warm water had entered deep cavities beneath it, melting the underside at a rate much higher than predicted. This melting caused the grounding line to retreat inland. As the grounding line moved, the ice above lost support. With less support, the shelf began moving faster. The increased movement created additional strain on the grounding points still anchoring it. These points eventually weakened too, causing the retreat to accelerate further. This pattern of acceleration and retreat was not unique to one shelf. Several showed similar behaviours, though at different rates. Some shelves lost thickness gradually. Others experienced sudden changes after years of stability. In the most extreme cases, entire sections of shelves broke off in large pieces. These events received media attention because of the size of the icebergs produced. But the iceberg formation wasn't the most significant concern. The concern was what happened afterward. Without the shelf slowing it, the glacier feeding into the region sped up, moving more ice toward the ocean. This increase in movement contributed to rising sea levels and revealed how dependent glaciers are on the shelves that hold them back. Scientists began studying the internal structure of shelves in more detail. They used radar to map layers within the ice, revealing fractures and weaknesses not visible from the surface. Some shelves had internal cracks that extended across long distances. Others had channels carved into their undersides by meltwater flowing from the interior of the continent. These internal features acted like structural weaknesses. If a shelf thinned too much, these weaknesses could propagate, leading to large-scale breakage. Even shelves that looked solid from above could contain fractures formed years earlier and waiting for the right combination of conditions to expand. Another surprising observation involved meltwater ponds forming on the surface of some shelves during warmer months. Even though surface temperatures in Antarctica are cold, certain regions experience enough sunlight during the summer to create small pools of meltwater. These ponds add weight to the surface. Because water is denser than ice, the added weight pushes downward, stressing the ice. If cracks exist beneath the water can travel into them, pushing the cracks wider. This process is called hydrofracturing. Once it begins, the progression is quick. Water pours into cracks, widening them further, allowing more water to enter. Eventually, the weight and pressure can cause a section of the shelf to fracture completely. Surface melting doesn't occur everywhere, but where it does, shelves become more vulnerable. Some shelves have experienced rapid disintegration following periods of intense surface melting. The most well-known example happened when an entire shelf collapsed within days, a process driven by a combination of thinning from below and hydrofracturing from above. Though dramatic, these collapses serve as reminders of how quickly shelves can change once certain thresholds are crossed. The hidden network of subglacial meltwater highways also plays a role in weakening shelves. Water flowing from beneath the interior of Antarctica can reach the base of shelves, carrying heat and creating small channels that erode the ice from below. These channels grow over time, sometimes forming long troughs along the underside. When enough channels appear, they weaken the overall structure. Some shelves show rows of surface depressions that correspond to channels beneath. These depressions act like floors that reduce resistance to bending, making the shelf more sensitive to stress. Even though these processes take place beneath the ice, satellites can detect the effects. Small changes in elevation, shifts in ice speed, and the development of fractures all provide clues. The combination of surface and subsurface data helps scientists piece together how shelves are changing. But even with modern tools, predicting the exact moment a shelf will shift or break remains difficult. Many shelves appear stable until they reach a tipping point. Once crossed, change happens rapidly. Ice shelves also behave differently depending on their location. East Antarctica contains shelves that are thicker and more stable, although some regions there have begun thinning in recent decades. West Antarctica contains shelves resting on deep basins that slope inland, making them more vulnerable. When a grounding line retreats into one of these basins, warm water can enter deeper regions, accelerating melting. This feedback loop has contributed to rapid changes in several glaciers. Another factor that complicates shelf behaviour is the strength of the ice itself. Ice might seem like a single material, but its properties vary. Crystal structure, density, and temperature all influence how it responds to stress. Ice that formed quickly may contain more air bubbles or be less dense. Ice that forms slowly may be stronger. Shelves containing a mix of ice types show varied responses to stress. Some areas buckle easily, others resist. Predicting how these mixed sections behave requires detailed study. The shifting of ice shelves also affects the environment around them. When a shelf thins, it changes the shape of the ocean cavity beneath. This allows warm water to circulate differently, sometimes allowing it to reach new areas. When a shelf breaks apart, it changes how icebergs form, how currents disperse fresh water, and how nutrients move through the Southern Ocean. Each of these changes influences marine ecosystems. Even though Antarctica seems distant from the rest of the world, its changes ripple outward in subtle ways. Scientists worry most about the shelves acting as gateways to glaciers that rest on bedrock far below sea level. These glaciers hold enough ice to raise global sea levels significantly if they destabilize. The shelves in front of them slow their flow, acting almost like dams. Weakening these shelves makes it easier for the glaciers to speed up. As the glaciers thin and retreat, the ocean reaches further inland, melting new ice from below. This cycle doesn't reverse easily. Once a glacier retreats into a deep basin, it becomes difficult to regain stability. Ice shelves that once held back massive amounts of ice suddenly become unable to perform that role. Another issue is the unpredictability of shelf response. Two shelves exposed to similar conditions may behave differently. One might thin gradually, another might break apart quickly. The presence of internal fractures, meltwater channels, grounding points, and cavities beneath the ice all influence how a shelf reacts. These features are not always visible or easy to map. Some are detected only after changes begin. The future of many ice shelves remains uncertain. Some may continue thinning for decades before showing signs of major instability. Others could reach thresholds sooner. As warm ocean water continues circulating beneath them, and as surface temperatures fluctuate, shelves will respond in their own ways. Some may form new cracks. Others may strengthen temporarily if snowfall increases. Each shelf is its own complex system influenced by multiple factors working together. The role of basal melting remains a central concern. Warmer water flowing into cavities beneath shelves carries enough energy to melt ice at significant rates. This water doesn't always move predictably. It can shift direction based on changes in wind patterns, ocean currents, or even the melting of other shelves. Once warm water finds a path under a shelf, it can remain there for long periods, carving deeper cavities. These cavities thin the shelf, making it more flexible and prone to fracture. Satellite observations show that once certain shelves begin thinning, the process accelerates. The shelves not only lose thickness but also spread out more quickly. This spreading increases tension, which leads to more fractures. These fractures may remain small at first but can grow rapidly under continued stress. Once fractures reach critical lengths, large pieces of ice can detach. What makes all of this especially important is the connection between shelves and the interior of the ice sheet. Shelves do not sit passively at the edge of the continent. They are part of a dynamic system. Their stability determines how quickly ice moves toward the ocean. When shelves weaken, glaciers behind them respond. They move faster, they stretch, they thin, and once they thin enough, they expose themselves to even more contact with warm water. These feedback loops explain why scientists use phrases like knife's edge when describing shelf stability. The shelves aren't failing everywhere at once, but some are approaching conditions that leave little margin for error. A slight change could shift the balance. A few more years of warm water circulation might hollow out critical regions. A single melting season with more surface water could stress the ice in ways that trigger fractures. Despite these concerns, it's important to understand that not all shelves are nearing collapse. Many remain thick, cold, and stable. Some even show signs of growing slightly due to increased snowfall. But for shelves in vulnerable regions, the combination of basal melting, fracture development, and grounding line retreat creates conditions that demand careful monitoring. As we move forward in this long exploration beneath the ice, the next part will turn attention to the hidden movements of the ocean itself. The water beneath these shelves moves in ways that influence everything above it. Understanding how that water flows, how it circulates, where it warms, where it cools, and how it interacts with the ice, reveals yet another layer of the complexity scientists are trying to understand. When scientists first tried to picture the water moving beneath Antarctica's ice shelves, they imagined something simple: a cold, quiet ocean sealed off from the rest of the world, barely shifting except when pushed by tides or small changes in temperature. But the more data they collected, the clearer it became that this hidden ocean does not sit still. It moves with patterns shaped by forces far beyond the ice sheet. It carries warmth in places where warmth shouldn't be. It funnels cold water downward in places where cold should dominate. It pulses through narrow channels, pools beneath vast shelves, rises along slopes, and circulates through cavities carved over decades. These movements happen constantly, even though the surface above may appear motionless. The ocean beneath Antarctica breathes in its own quiet way, following rhythms that influence the entire ice sheet. To understand why this movement matters, it helps to think about how water carries energy. A small change in water temperature may not seem like much, but even a slight increase in warmth can melt ice from below at rates that reshape entire regions. The difference between water a few degrees above freezing and water right at the freezing point is enough to determine whether an ice shelf remains stable or begins to weaken. The challenge is that warm water doesn't disperse evenly beneath the shelves. It finds pathways shaped by underwater ridges, deep channels, and the contours of the ice itself. These pathways guide the water, sometimes steering it towards sensitive grounding lines where even minor melting can trigger larger changes. One of the earliest clues that this hidden ocean was active came from observations of uneven thinning along the base of ice shelves. Some areas thinned rapidly, while others nearby showed only small changes. This variation suggested that warm water was not spreading evenly, but instead following specific routes. When scientists used instruments lowered through holes drilled in the ice, they found currents moving with surprising speed through the cavities beneath. These currents sometimes carried water warmer than expected for the region. The warmth was subtle but enough to explain the rapid basal melting observed in satellite measurements. This warm water often originates from deeper parts of the Southern Ocean, where it circulates around Antarctica in a massive current known for its strength and persistence. This current carries water that retains heat, accumulated thousands of kilometers away. When wind patterns shift or sea ice changes, the current can push this warmer water closer to the continent. Once there, it can sink below the cold surface layer and find its way into sub-ice cavities. It doesn't arrive in dramatic surges. Instead, it creeps inward over time, guided by the shape of the seafloor and the openings beneath the shelves. This movement is influenced by the Earth's rotation, which causes currents to bend and curve rather than move in straight lines. The rotation steers water in ways that create looping patterns beneath the ice. In some areas, these loops bring warm water deep under shelves. In others, they push cold water outward. The result is an ever-changing circulation system that reacts to shifts in wind, sea ice, and atmospheric conditions happening far from the ice sheet. Another factor shaping these rhythms is the presence of underwater ridges. These ridges act like barriers, redirecting currents and forcing water to rise or fall. When warm water encounters a ridge, it may be pushed upward toward the base of an ice shelf. Even a slight rise is enough for that water to begin melting ice. Once melting starts, it can widen the cavity, making it easier for more water to enter. This feedback loop results in deeper cavities that support stronger circulation patterns. Eventually, the cavity may grow large enough to change how the shelf above moves. The ocean also responds to the tides. While the ice shelves appear massive and immovable, tides lift and lower them slightly each day. This movement affects the water beneath them, drawing water in and out of cavities. The daily shifting of water may not be visible on the surface, but beneath the shelves, it can influence how warm water flows. Some measurements show that tidal cycles help pump water through narrow channels, pushing warmth into areas that might otherwise remain isolated. Even though the tidal lift is small, the effect on circulation can be significant over long periods. One of the most interesting discoveries about this hidden ocean is how mixing occurs within the cavities. Warm water entering from the deep ocean often rises toward the ice. As it melts the ice above, the meltwater produced is colder and fresher than the ocean water. This fresh meltwater then sinks lower or moves outward depending on the local shape of the cavity. As it moves, it mixes with surrounding water, redistributing heat and affecting how the cavity evolves. This mixing is not uniform. Some regions experience strong turbulence, others remain relatively calm. These differences in mixing help explain why melting rates vary across the underside of a single shelf. Another surprising factor shaping the movement of this hidden ocean involves interactions with melting from the continent's interior. When meltwater highways carry water from far inland toward the coast, that water eventually enters ocean cavities beneath shelves. Even small amounts of fresh water can alter circulation patterns by changing the density of water layers. Freshwater is less dense than seawater, so it tends to rise. This rise pushes warmer water downward or sideways, adjusting the overall circulation. Over time, these subtle adjustments can redirect warm currents towards sensitive parts of an ice shelf. Researchers studying these circulation systems have suggested that some shelves function like large lungs. They inhale warm water during certain seasons or wind conditions and exhale it at others. These cycles occur slowly but consistently. They determine how much heat reaches the grounding line and how quickly cavities grow. What makes these cycles concerning is that small changes in wind patterns or sea ice can shift the timing or intensity of this breathing. A slight strengthening of winds circling the continent can push more warm water beneath shelves. A small reduction in sea ice can change how surface water cools, affecting how water sinks or rises. Wind plays an especially important role in shaping these rhythms. Winds around Antarctica influence how surface waters move and how deep currents rise. When winds strengthen, they can cause deeper, warmer water to rise toward the surface. This process, known as upwelling, increases the amount of warm water available to enter cavities beneath shelves. Even if the wind change is temporary, the effects on circulation can last for months or years. Once warm water finds a pathway under a shelf, it tends to stay there until larger environmental shifts force it out. Changes in the amount of sea ice also matter. Sea ice acts as an insulating layer that prevents the ocean from losing heat quickly. When sea ice coverage decreases, more heat escapes into the atmosphere. This cooling can cause surface water to sink, pushing deeper water upward. Depending on local conditions, the deeper water may be warmer than the surface layer it replaces. These interactions highlight how distant changes can influence what happens beneath the ice shelves. Another factor that affects circulation is the shape of the seabed beneath the shelves. Some areas contain deep troughs that act like channels guiding warm water far inland. These troughs can extend under grounding lines, allowing water to reach places once thought unreachable. If warm water reaches these grounding lines, it can melt ice from below, leading to retreat. Other regions contain high ridges that block water movement. These ridges once provided natural protection for ice shelves, but as shelves thin and grounding lines retreat, even these protective features may become less effective. Scientists also study how small-scale processes influence circulation. Tiny eddies, only tens of meters across, can mix water layers in ways that affect heat distribution. Even though these eddies are small compared to the size of an ice shelf, their cumulative effect is significant. They help determine how quickly warm water spreads and how thoroughly it mixes with colder water. Understanding these processes requires detailed measurements and sophisticated models, because they are too small to observe directly with satellites. The presence of meltwater channels beneath shelves also affects how the ocean moves. These channels serve as routes for warm water to travel farther inland. As channels enlarge, they may allow more water to flow through. Some channels become large enough to influence the shape of the cavity itself. When channels deepen, they can guide currents into new regions, increasing melting in areas that previously remained cold. These interactions show how circulation and cavity structure evolve together. One of the more subtle effects of circulation occurs when warm water melts ice that contains trapped air. As this ice melts, the air is released into the water. Tiny bubbles rise toward the top of the cavity, altering how water moves. These bubbles may not change circulation dramatically, but they add another layer of complexity to a system already influenced by countless small interactions. Another surprising discovery came from observing how the hidden ocean reacts to seasonal changes far from Antarctica. Storm patterns in the southern hemisphere, shifts in atmospheric pressure, and temperature changes in distant regions all influence how warm water moves around the continent. Even though Antarctica feels isolated from global climate patterns, it is connected through the ocean. This global influence means that events thousands of kilometers away can ripple beneath ice shelves. Researchers began to use floats, buoyancy-controlled instruments that drift with ocean currents, to measure water movement beneath shelves. These floats detected rising and falling temperatures, changes in salinity, and shifts in current direction that suggested a constantly adjusting system. Some floats recorded multiple circulation cycles within a single year. Others drifted into deeper cavities and remained there until they surfaced months later with new data. These floats helped scientists map circulation patterns that were previously impossible to study. But even with these tools, much of the hidden ocean remains unknown. Many cavities are too deep or narrow for instruments to enter safely. Some areas contain currents too strong or unpredictable for equipment to handle. As a result, models remain essential. These models simulate water movement based on factors like temperature, salinity, pressure, and cavity shape. Each new observation helps refine the models, but uncertainties remain. The hidden ocean's breathing patterns are complex, and predicting them requires understanding both global climate systems and local features beneath the ice. What makes this ocean so important is its influence on the stability of the ice shelves above it. If circulation patterns continue directing warm water toward grounding lines, shelves may weaken more quickly. If winds strengthen or sea ice continues changing, circulation may intensify. Some shelves might withstand these shifts for decades. Others may approach tipping points sooner. Predicting which shelf will respond and how remains a challenge. Despite the difficulties, studying these rhythms offers a clearer picture of how the entire Antarctic system functions. The hidden ocean acts as a mediator between the deep sea and the ice sheet. It transfers heat, redistributes fresh water, and shapes the cavities beneath the ice. Its movements may be silent to the human ear, but they carry consequences that reach far beyond Antarctica. As we continue through this story beneath the ice, the next part turns from movement to memory, the clues locked within salt, stone, and silence. These clues reveal how long these cycles have been unfolding and what the continent has endured before. They help scientists understand the history of Antarctica's changing environment and what that history suggests for the future. When scientists study Antarctica's hidden world, they rely not only on present-day measurements, but also on clues frozen into the landscape over long stretches of time. The continent holds a memory of what it has been through, although it doesn't reveal this memory easily. Every grain of sediment, every pattern of salt trapped within ice, every subtle shift in rock beneath the sheet, carries a record of past conditions. The challenge is understanding these records without disturbing the fragile environments that hold them. Antarctica doesn't speak in clear events or visible patterns. It speaks slowly, through small accumulations that built up over thousands or millions of years. And it is within this silence that scientists search for signs of how the ice behaved before, how the oceans moved, and how the landscape responded to changes similar to those happening today. One of the first places researchers look for clues is in the sediment resting at the bottom of subglacial lakes. These lakes, sealed off from the atmosphere, collect layers of material that sink slowly from the ice above or wash in through meltwater channels. The layers form thin bands, each representing a period when different conditions dominated the lake. Some layers contain fine particles carried downward through the ice. Others show the presence of ancient organic matter that settled there before the region froze. By examining the chemical composition of these layers, scientists can infer when melting increased, when water drained, and when nutrients were more abundant. Each band acts like a short entry in a long journal. Reading these entries takes time, but they reveal patterns no instrument alone can show. Sediment composition also carries clues about the underlying bedrock. If certain minerals appear more frequently at one time than another, researchers can infer that water flowed from a different region, or that ice movement exposed new surfaces. For example, if a lake suddenly contains minerals found only in rocks far upstream, this suggests that meltwater highways redirected flow at that time. These shifts may indicate stress changes in the ice sheet, or periods of increased melting triggered by heat rising from below or water entering from the coast. In this way, sediment becomes a map not only of lake history, but of the movement of water across the continent's underside. Another key source of information lies in the salt trapped within ice cores. Even though Antarctica is known for its freshwater ice, tiny amounts of salt can appear deep within the sheet. These salts come from ancient seawater that once reached areas now buried beneath kilometres of ice, or from atmospheric particles carried by wind long before the ice formed. By analysing the types of salts and their concentration, scientists can reconstruct when certain regions were connected to the ocean. If a layer of ice contains salt signatures matching seawater, it suggests that the ice may have formed during a time when the coastline looked entirely different. These findings help researchers understand how far the ice extended during past glaciations, and how much the ocean rose or fell over different periods. Salt also plays another role. The way it settles in certain layers can reveal changes in temperature and the movement of water. Salt trapped in freezing seawater behaves differently than salt trapped in melting ice. By studying these patterns, scientists can determine whether ice was expanding or retreating at the time the salts became embedded. In some cases, subtle differences in salt composition reveal temporary warm periods that occurred long before humans recorded climate variations. These warm periods may offer clues about how sensitive the ice sheet is to temperature changes. Rock beneath the ice tells another part of the story. When seismic instruments send vibrations through the ice, the waves move differently depending on what lies below. By studying how these waves travel, scientists can infer whether the bedrock is hard, soft, fractured, or smooth. Soft sediments indicate areas where water once pooled. Hard polished rock suggests long periods of ice flow. Fractured rock may reveal ancient earthquakes, tectonic activity, or interactions between the crust and deep mantle heat. Each variation helps build a picture of the continent's long-term stability. Some regions appear far older and more stable than others. Others reveal evidence of movement that occurred repeatedly over millions of years. A particularly interesting discovery came from areas where the bedrock sits far below sea level. These deep basins indicate that parts of the continent were once free of ice, allowing erosion to carve out valleys and channels. Later, as the ice sheet formed and grew, it filled these basins, covering landscapes that once resembled open plains or fjord-like coastlines. The shape of these basins influences how water moves beneath the ice today. Warm water tends to flow into them more easily, causing increased melting. Understanding the depth and shape of these basins helps scientists predict how vulnerable certain glaciers might be to retreat. The thickness of sediment also reveals how long water has occupied certain areas. In regions where meltwater flows constantly, sediment tends to be thin. Water washes away particles before they can accumulate. In contrast, thick layers of sediment indicate long-standing lakes that change slowly over time. These lakes may contain some of the oldest microbial ecosystems beneath Antarctica. Their sediment acts like a time capsule, storing evidence of biological activity that has persisted for astonishing lengths of time. Chemical clues in meltwater itself reveal additional details. The concentration of dissolved minerals, gases, and organic compounds tells researchers where the water came from, how long it stayed underground, and what it encountered along the way. For example, meltwater with high concentrations of certain minerals may have travelled through heated rock, picking up signs of geothermal influence. Meltwater with significant organic carbon may have originated in areas containing buried remains of ancient life. High levels of dissolved gases might indicate melting of old ice that carried pockets of trapped air. Even the temperature of meltwater carries valuable information. Water slightly warmer than expected may point to increased friction from ice movement or the presence of hidden geothermal hotspots. Cooler meltwater may suggest drainage from far inland regions where geothermal activity is weaker. Tracking these temperature differences helps scientists map unseen heat sources beneath the ice. Another key record comes from the shape of the ice itself. Satellite measurements show how the surface rises and falls over time. These changes reveal processes occurring deep beneath the sheet. When a subglacial lake fills, the ice above it rises. When it drains, the ice sinks. These changes are subtle, often measured in centimetres, but they tell scientists how water is moving below. Long sequences of rises and falls across a lake's surface can reveal a history of drainage events stretching back decades or even centuries. By combining these surface observations with radar and seismic data, researchers create a detailed timeline of water movement across the continent's hidden network. These vertical movements also reveal which lakes are connected. When two lakes rise and fall in synchronized patterns, they likely share a connection through meltwater channels. Understanding these connections helps scientists trace the pathways water takes as it travels beneath the ice. These pathways, once charted, reveal how the subglacial landscape responds to pressure, melting, and subtle temperature changes. Another clue lies in minerals that form under specific chemical conditions. Some minerals, such as iron oxides or calcium carbonates, form only when certain microbes are present. Their presence in sediment layers reveals which biological processes dominated at different times. If a layer contains minerals associated with iron metabolizing microbes, this suggests that iron-based metabolism was particularly active during that period. If another layer contains minerals formed by sulfate-reducing organisms, researchers can infer that conditions favoured a different form of energy production. These clues help reconstruct how microbial communities evolved over time, responding to changes in water chemistry and nutrient availability. In some lakes, chemical signatures indicate periods when oxygen levels were higher or lower. These shifts often correspond to changes in water flow or periods when the lake connected to other basins. High oxygen levels may indicate a time when meltwater brought more oxygen-rich ice into the basin. Low levels may reflect long periods of isolation, when microbes consumed available oxygen faster than it could be replenished. Each of these shifts leaves a mark in the sediment, allowing scientists to trace the lake's history, even when direct observation is impossible. The silence of the environment provides another subtle but important source of information. Because the continent lacks the noise and movement common in other regions, seismic instruments can pick up extremely faint vibrations. These vibrations reveal cracks forming deep within the ice, water moving through channels, or small shifts in sediment beneath glaciers. Over long periods, these seismic records reveal patterns of movement that would otherwise go unnoticed. Some regions show frequent micro-movements that suggest active water flow. Others remain quiet for long periods, indicating stability. Seismic records also reveal how ice shelves respond to forces beneath them. When warm water flows into a cavity, the shelf may flex slightly. This flexing produces vibrations that instruments can detect. By analysing these vibrations, scientists can determine how quickly cavities are expanding and which parts of the shelf are most affected. These measurements build on earlier findings from radar and satellite observations, adding another layer of understanding to the hidden environment. Another important clue comes from analysing the oxygen and hydrogen isotopes within water trapped in ice. These isotopes vary depending on where and when the water originally fell as snow. By measuring isotope ratios, scientists can determine whether certain ice layers formed during warmer or colder periods. These measurements reveal cycles of climate variation that extend back hundreds of thousands of years. They show periods when the ice sheet advanced or retreated, when snowfall increased or decreased, and how temperature trends shifted over time. These isotope records also help researchers predict how the ice sheet might respond to modern warming. If past warming events cause significant retreat, similar responses might occur again. If the ice sheet persisted through warm periods without major collapse, that history offers a different type of insight. Either way, the isotopes provide a long view of the continent's behaviour that cannot be gathered through modern observations alone. The rocks beneath Antarctica contain another silent archive. In certain regions, the bedrock shows signs of having been exposed to the atmosphere long ago before ice covered it. These rocks contain chemical markers formed when they sat in open air. By detecting these markers, scientists can estimate how long the rock remained exposed and when the ice eventually buried it. This method helps reconstruct ancient glacial movements, Some rocks show exposure ages of millions of years, indicating that ice once melted far back from its present boundary. Others show that the ice sheet remained present in certain regions throughout multiple climate cycles. These records reveal that Antarctica's ice sheet has not always been as extensive as it is now. There have been times when large portions of the continent were ice-free, and others when the ice grew massively. Understanding these cycles helps scientists evaluate the potential future of the ice sheet under modern warming conditions. While the past cannot predict the future perfectly, it provides a framework for understanding how the continent responds to natural climate shifts. Clues also come from the chemistry of relic seawater trapped beneath the ice. In regions where the ocean once extended further inland, pockets of ancient seawater remain sealed beneath glaciers. This water contains chemical signatures from long past climates. Comparing these signatures with modern seawater helps determine when the ocean last reached those areas and how conditions differed at the time. These findings inform models that track how vulnerable current grounding lines might be to intrusion by warm ocean water. Each of these clues, sediment layers, salt patterns, seismic vibrations, mineral formations, isotope ratios, and chemical signatures, speaks in its own quiet way. They reveal patterns that emerge only when viewed over long periods. They show that the continent has endured cycles of warmth and cold, stability and retreat. They show that water has reshaped the landscape repeatedly, and that life has persisted even through dramatic environmental changes. As we continue into the next part of the story, attention shifts to the future unfolding beneath our feet. All these clues help scientists understand the past, but they also shape their understanding of what the ice sheet might face next. The hidden ocean, the caverns, the meltwater networks, and the deep heat sources all interact in ways that determine how the ice will respond to the world above it. When scientists try to understand where Antarctica is heading, they do not start by imagining a single future. Instead, they consider a range of possibilities shaped by how ice, water, heat, and pressure interact in ways that are far from simple. For a long time, the continent was assumed to be slow to respond to change. Its size, its cold temperatures, and the thickness of the ice sheet created a sense that whatever shifts occurred would take ages to unfold. But evidence gathered from the hidden landscape beneath the surface tells a different story. It shows a continent more sensitive than previously believed. It reveals systems that can accelerate once certain thresholds are crossed. It shows an ocean delivering warmth into places once considered unreachable. And it shows meltwater moving in ways that can reshape entire regions without leaving a trace on the surface until the effects have already grown significant. These discoveries create a new challenge, trying to understand how the future might unfold when the ground beneath the ice is shifting, quite literally, in ways that nobody imagined decades ago. This future is not defined by a single dramatic moment. It forms through gradual adjustments that build on one another. Each small change, whether in ocean temperature, grounding line position, subglacial water flow, or surface melt, has the potential to influence processes more deeply within the ice sheet. It is the accumulation of these changes that determines how the continent responds. One of the strongest signals comes from ice shelves. These floating extensions of the ice sheet hold back glaciers that rest inland on bedrock far below sea level. When shelves remain stable, they slow the ice behind them. When shelves thin or fracture, the restraint weakens. Over time, glaciers begin moving faster. These faster flows deliver more ice to the ocean. They deepen grounding lines. They expose new areas of ice to warm water, and once the grounding line retreats into deeper basins, the glacier becomes more vulnerable. The future of certain regions may hinge on whether the shelves in front of them can maintain their structure long enough for the climate to stabilize. Some shelves already show signs of thinning at rates that exceed earlier estimates. The thinning does not occur evenly. It follows patterns shaped by warm water entering from below and meltwater channels delivering fresh water from above. Even a small opening beneath the north-facing edge of a shelf can widen into a cavity that grows steadily as warm water circulates inside it. Once that cavity expands to a certain size, it can set the shelf onto a path that leads to long-term weakening. For glaciers that sit on bedrock sloping downward inland, this transition holds particular importance. Once the grounding line retreats into deeper regions, it becomes difficult to reverse the trend. The deeper the bedrock valley, the easier it is for warm water to enter and melt more ice from below. Several glaciers in West Antarctica occupy such basins. If their grounding lines continue retreating, they may reach points where feedback loops accelerate ice loss. These loops do not rely on surface temperature alone. They rely on the shape of the ground, the movement of water beneath the shelves, and the warmth entering from the ocean. Another area of concern involves the distribution of geothermal heat beneath the continent. For years, geothermal heating was considered a minor factor compared to surface climate. But new measurements show that its influence varies widely across different regions. Some hotspots lie directly beneath glaciers already thinning from above. When geothermal heat increases melting at the base, the glacier loses additional stability. As more water forms between ice and bedrock, friction decreases. The glacier begins sliding more easily. Faster sliding leads to more friction in certain areas, which generates additional heat. This extra heat melts even more ice. What begins as a subtle interaction can grow into a significant process that changes the glacier's behaviour. The movement of subglacial meltwater also shapes the future. Meltwater highways, which were once thought to be rare or insignificant, appear throughout large areas of the continent. These channels guide water from one basin to another, sometimes travelling hundreds of kilometres under the ice. As water flows through them, it can erode sediment, widen the channels, and alter the base of the ice sheet. These changes influence how ice moves above. A glacier sliding over wet sediment can behave very differently from one sliding over dry rock. Small shifts in meltwater distribution may change glacier speed in ways that become noticeable only after years of cumulative movement. Subglacial lakes add another dimension. These lakes fill and drain repeatedly, raising and lowering the ice above them. When they drain suddenly, the water can travel along new pathways, forcing rapid adjustments in the surrounding ice. These drainage events do not necessarily signal impending collapse, but they demonstrate how interconnected the hidden system is. A change in one lake can influence conditions far downstream, altering how water accumulates beneath shelves or how grounding lines shift. The hidden caverns beneath the ice contribute their own uncertainties. These large voids, some big enough to rival urban structures, reduce contact between ice and bedrock. Reduced contact decreases friction. This allows the ice above to move more freely. As these caverns grow, they may cause sections of the ice to sag or crack. Even slight changes in sagging can alter how stress distributes across a glacier. Some caverns may drain quickly during meltwater surges. Others may expand slowly as warm water continues carving them wider. Each scenario affects the stability of ice above. Future changes also depend on how the ocean continues moving heat toward the continent. The ocean's circulation around Antarctica is powerful, but its patterns are sensitive to winds, surface temperature, and the presence of sea ice. Recent years have shown shifts in wind patterns that bring deeper, warmer waters upward. When this water reaches underwater troughs leading beneath ice shelves, it becomes a potent source of basal melting. If wind patterns continue changing, more warm water may enter sub-ice cavities. The degree to which this happens will determine how quickly some shelves thin. Another challenge comes from changes in sea ice. Sea ice helps regulate how much heat the ocean loses to the atmosphere. As sea ice coverage fluctuates, the rate of ocean cooling changes. Less sea ice allows more heat to escape, which can cause circulation patterns to shift. These shifts may influence how much warm water moves toward the continent. In years with lower sea ice extent, the ocean may warm slightly beneath the surface layer, giving warm water more opportunities to reach grounding lines. Yet not all parts of Antarctica will change at the same pace. The continent is vast and its underlying conditions vary widely. Some regions sit on stable bedrock far above sea level, making them less vulnerable to ocean intrusion. Others rest on deep basins carved by ancient forces. The glaciers in these basins are already in contact with seawater at their grounding lines, making them more sensitive to changes in warm water flow. The future of the ice sheet depends on how each region responds individually and how these responses interact with one another. In some areas, additional snowfall may temporarily thicken the ice. Increased snowfall can help offset thinning in certain regions, at least for a time, but thicker snow does not strengthen the base of glaciers. If melting continues beneath the ice, or if warm water reaches grounding lines, surface thickening may not compensate for basal loss. The balance between snowfall and basal melting determines whether a glacier grows or retreats, and this balance is becoming harder to predict as environmental conditions shift in multiple directions at once. Sea level rise presents another central concern. As glaciers accelerate and grounding lines retreat, more ice enters the ocean. Some of this ice is already floating, so its melting does not significantly affect sea level. But ice that sits on bedrock contributes directly to sea level rise when it flows into the ocean. Several glaciers in West Antarctica contain enough ice to raise global sea level by considerable amounts if they lose stability. Even partial retreat in these regions could produce meaningful impacts around the world. Beyond these large-scale processes, smaller changes also shape the future. Cracks forming on the surface of ice shelves can widen under repeated stress. Channels forming beneath shelves can merge or deepen, weakening the ice above them. Even minor increases in meltwater flow can shift how pressure is distributed across the base of the ice sheet. These seemingly small interactions add up, gradually pushing systems toward new states. Despite these uncertainties, Antarctica does not face a single predetermined outcome. Scientists continue refining models to understand how sensitive certain regions are, how quickly warming might reach vulnerable areas, and which processes are most likely to accelerate. These models draw on decades of measurements: surface elevation, grounding line position, ice speed, ocean temperature, sediment composition, and seismic vibrations. Each new dataset strengthens the understanding of how the continent behaves under changing conditions. Emerging technologies also help reduce uncertainties. Autonomous underwater vehicles can travel beneath ice shelves to map cavities and measure water properties. Satellite missions track ice thickness and movement with increasing accuracy. Drilling systems allow cleaner access to subglacial lakes and meltwater channels. These tools provide a clearer picture of how the hidden world beneath the ice functions, giving scientists the information needed to refine predictions. One of the most important insights gained from recent work is that Antarctica does not respond slowly to all changes. Some processes unfold over centuries, others happen within years or even months. When ice shelves thin past a certain point, they can fracture quickly. When warm water enters a new cavity, melting can accelerate unexpectedly. When a meltwater channel widens, it can redirect flow and reshape parts of the hidden network. These non-linear responses, changes that accelerate once thresholds are crossed, make the future difficult to predict with certainty. But they also highlight which regions require close monitoring. Another key insight involves the role of feedback loops. Once a glacier begins retreating into a deep basin, warm water follows. As warm water melts more ice, the basin becomes deeper. As the basin deepens, the grounding line retreats. Each step reinforces the next. These loops can drive glaciers into long-term retreat. They do not reverse easily. Understanding how close certain regions are to entering these loops helps scientists assess long-term stability. Even with these concerns, it is important to recognize that large portions of Antarctica remain stable for now. Some shelves show minimal thinning. Some glaciers show movement consistent with natural variability. The eastern part of the continent contains enormous volumes of ice resting on high bedrock, making it less vulnerable than the west. The future will likely involve a mix of stability and change, with some regions shifting rapidly while others remain slow to respond. The broader picture reveals a continent shaped by both ancient forces and modern changes. Its hidden lakes, meltwater networks, geothermal hotspots, and deep caverns form a complex system influenced by factors operating on different timescales. The challenge is understanding how these factors interact as the planet warms. Some processes respond directly to temperature increases. Others respond to changes in ocean circulation or pressure distribution. Still others respond to the structure of the hidden landscape beneath the ice. These interactions form the stage upon which the next chapter unfolds. A chapter shaped not just by scientific questions, but by the quiet acknowledgement that Antarctica's transformation has consequences far beyond its frozen borders. As this journey continues, the story turns to the quiet discussions happening among scientists themselves. They understand how much remains uncertain, yet they see patterns emerging. Their concerns are not based on dramatic predictions, but on the weight of evidence showing how sensitive the continent truly is. When scientists gather to talk about Antarctica, the conversations are often measured. They speak carefully, not because they are trying to hide anything, but because the continent itself demands caution. It is a place where changes happen in ways that are not always obvious until they have already grown large. It is a place built on the kind of scale that makes even the most confident predictions feel tentative, and it is a place where new discoveries appear often enough that certainty becomes something handled sparingly. Yet within these careful conversations there is a quiet truth that many scientists share when the microphones are off, and the discussions shift away from formal reports. It is the recognition that the hidden world beneath the ice is not merely a curiosity. It is a crucial part of how the continent is changing, and it is changing faster than earlier generations ever expected. This truth doesn't come from a single dramatic finding. It comes from dozens of smaller ones, each revealing another piece of a system that is more complex than once imagined. Radar surveys show meltwater channels stretching farther than predicted. Seismic measurements detect cavities forming in places believed to be stable. Ocean instruments track warm currents moving beneath shelves that were assumed to be cold at their base. Sediment cores reveal long histories of water movement that defy simple explanations. Microbial samples show communities that persist through isolation and shifting conditions. Together, these details form a picture of a continent responding to stress in ways that are subtle but unmistakable. Scientists talk quietly about how the ice sheet behaves when warm water reaches grounding lines. They have watched the lines retreat in areas once believed to be secure. They have seen glaciers speed up when ice shelves thin. They have measured the rate at which some shelves lose thickness, and realised that the numbers exceed those built into earlier models. They know that for glaciers sitting on deep basins, warming at the grounding line can start a cycle that feeds into itself. And while they emphasise that these changes do not mean sudden collapse, they also recognise that the direction of change matters as much as the speed. Another truth scientists discuss is how unpredictable some processes remain, even with decades of data. Meltwater beneath the ice moves through channels that shift with pressure, heat, and time. Lakes fill and drain without warning, influencing ice movement in ways that are difficult to forecast. Some regions experience rapid melting from warm water delivered through deep ocean currents, while others remain stable because local conditions shield them. Predicting which region will change next is not straightforward. Antarctica does not respond uniformly. It responds in patches, each following its own path based on local conditions. There is also an awareness that Antarctica is not isolated from the rest of the planet. Winds far away can change how warm water circulates near the continent. Shifts in sea ice influence how much heat the ocean loses. Variations in ocean currents shape where warm water rises and where it sinks. Even storm patterns in the southern hemisphere can alter how much warmth reaches the underside of ice shelves. This interconnectedness means that the future of Antarctica is tied to systems operating across the planet. small changes elsewhere may eventually influence the hidden ocean beneath the ice. One of the quieter concerns scientists express involves the difficulty of monitoring the hidden world at the scale needed to understand it fully. Much of what happens beneath the ice cannot be observed directly. Instruments travel only so far. Drilling accesses only tiny areas. Radar and seismic methods reveal broad features but not always the details. Satellites show changes at the surface, but not what triggered them deep below. This limited access means that researchers must piece together clues from multiple sources, hoping to construct accurate narratives from sparse data. They know that the continent still holds surprises, some that may ease concerns, others that may amplify them. Among the most whispered truths is that Antarctica has thresholds. These thresholds aren't dramatic or theatrical. They are quiet boundaries the system crosses when warm water reaches a grounding line, when a shelf thins past a key point, or when a cavity expands enough to change stress distribution. Once a threshold is crossed, the system may behave differently. It may move into a state where retreat accelerates, or where glaciers slide more easily. These thresholds do not come with clear warnings. They become visible only after the shift has started, which is why scientists speak about them with caution. Another point often discussed quietly is how much of the future depends on subtle feedback loops. A glacier speeds up, which generates more friction and heat, which melts more ice at its base, which lowers friction in another area, which speeds the glacier again. Warm water deepens a cavity, which draws in more warm water, which deepens the cavity even further. Surface melting finds a crack, which widens as water fills it, which allows more surface water to enter, which expands the crack still more. None of these loops operate quickly on their own, but over time they can produce meaningful changes that are difficult to reverse. Scientists also acknowledge the part of the story that does not receive as much attention. The resilience still visible in parts of the continent. Some shelves remain thick and stable. Some regions continue accumulating snow at rates that previously held steady for centuries. Portions of the bedrock sit high enough to resist intrusion by warm ocean water, and some glaciers move slowly enough that even moderate warming does not alter their behaviour dramatically. These pockets of stability matter because they show that Antarctica is not uniformly vulnerable. Yet they also highlight a contrast with more sensitive regions where changes are already underway. In private conversations, many researchers talk about how long it took to appreciate the importance of the hidden network beneath the ice. The subglacial lakes, the meltwater channels, the caverns carved by warm currents, the microbial ecosystems that alter sediment chemistry, all of these features contribute to how the ice moves and responds to stress. Earlier generations lacked the tools to see much of this. They assumed the base of the ice sheet was a uniform, frozen boundary, where water played only a minor role. Today, those assumptions no longer hold. Beneath the ice lies a landscape filled with motion, heat, and gradual change. There is also awareness that the public often seeks simple explanations, but Antarctica does not lend itself to simplicity. It contains processes that unfold on timescales too long for direct observation. It contains responses that accelerate only after boundaries are crossed. It contains hidden features that influence major outcomes without revealing themselves easily. This complexity shapes how scientists communicate. They try to convey that change is real, evidence-based, and significant, while also acknowledging the uncertainties and ranges of possible futures. Another topic that arises is the challenge of creating accurate models when so many variables interact at once. Models must consider the shape of the bedrock, the thickness of ice, the flow of warm ocean currents, the distribution of geothermal heat, the movement of meltwater, the formation of cavities, the behaviour of ice shelves, and the atmospheric conditions above. Each of these components contains its own uncertainties. Bringing them together into a single projection is extraordinarily difficult. Yet despite this difficulty, many models show similar trends: increased thinning in certain regions, continued retreat of grounding lines in deep basins, expansion of ocean cavities beneath shelves, and more rapid flow of vulnerable glaciers. Some of the most experienced researchers speak quietly about the emotional dimension of studying a place like Antarctica. They describe the weight of knowing that the continent is changing in ways that may reshape coastlines far from the ice. They describe the strange mix of awe and concern that comes from watching a glacier tens of kilometers wide shift perceptibly over just a few years. They describe the tension between scientific detachment and the recognition that these changes carry consequences not restricted to the polar regions. Yet these same scientists also speak about a deep respect for the continent's complexity. Antarctica is not simply melting. It is shifting, adapting, and responding to a combination of influences acting at multiple depths and scales. Its future will not unfold evenly. It may bring surprises both concerning and encouraging. The most important truth is that scientists continue learning, and each discovery sharpens the understanding of how interconnected the ice, ocean, and underlying landscape truly are. A recurring point in these quiet conversations is that Antarctica remains partly unknown. Even with modern tools, vast regions of the subglacial environment are unmapped. Many lakes have never been sampled. Many meltwater pathways remain invisible except for the subtle movements they create at the surface. Many cavities beneath ice shelves exist only as faint hints in radar reflections. Even the temperature distribution beneath the ice sheet is still being revealed. In this partial mystery lies a mixture of caution and curiosity. Scientists know enough to understand the stakes, yet not enough to claim certainty about every detail. One truth that emerges from all these discussions is that Antarctica's transformation is not isolated to dramatic events that capture attention for a moment. Instead, it is a pattern unfolding in slow steps. Each step influences the next. Caverns grow deeper, water finds new pathways, grounding lines shift, shelves thin, glaciers accelerate, and with each of these changes the shape of the continent adjusts. The adjustments may seem small individually, but together they determine the direction of the ice sheet's future. Another truth scientists whisper is that the continent often reacts before anyone notices. A cavity begins forming years before it appears in radar. A grounding line retreats meters at a time before satellites detect the shift. A meltwater channel widens slowly underground long before its influence becomes visible. By the time evidence appears on the surface, the process has already been underway. This lag complicates prediction. It also underscores why scientists treat early signs with seriousness, even when those signs seem small. Despite uncertainty, scientists do not speak about Antarctica with despair. They emphasize that understanding the continent is improving faster than ever. They highlight the technological advances that allow them to see beneath ice that once obscured everything. They talk about international collaborations that bring expertise from many fields into one effort aimed at understanding the whole system. They recognize that predictions will improve as more data becomes available and as models incorporate more realistic representations of the processes at work. There is also a sense of determination. Antarctica teaches patience. It requires long-term observation. It requires listening to signals that often seem faint at first, and it requires accepting that complexity does not imply hopelessness, only that caution and persistence are necessary. As scientists share these truths among themselves, they also acknowledge that the continent has more to reveal. The hidden ocean will continue circulating beneath ice shelves, reshaping cavities that grow and merge. Meltwater will continue finding new paths across the bedrock. Caverns will expand where warm water accumulates. Microbial communities will persist in their slow and steady way. And the ice will continue responding to pressures, temperatures, and forces above and below. None of these processes end abruptly. They continue into the future, shaping a continent that remains in many ways only partly understood. The quiet truth whispered about Antarctica is not a prediction of sudden catastrophe. It is the recognition that the systems beneath the ice are active, interconnected, and sensitive to change, and that understanding them, truly understanding them, requires patience, humility, and constant attention. As this exploration reaches its end for now, the story beneath the ice continues without pause. The currents keep moving, the lakes keep filling and draining, the caverns keep widening, and the clues hidden in the silence keep accumulating. The continent watches the world above it shift, and in its own slow and steady way, it shifts in return, never quite still, never quite simple, and never entirely revealed.